We are having a few more technical things to take care of until we start, so it will be maybe 2 minutes late. Just give us a second, please.
Hello, can you hear me?
Yes, Luis, sounds good.
Thank you very much.
All right, good morning and welcome everybody to the OYPT finals. I see that our teams are already here with their cameras on. We will take quite a few minutes to go over a few details about the finals, so we're not in a hurry at all. So my name is Michael. I'm the acting organizer of the OYPT, and I will give you a short introduction into the finals until Felicia, who has volunteered to be chair today, will take over and do the fighting moderation. So thank you very much for that. But before we go into that, I would like to do a few final remarks. So first of all, can somebody please drop into the chat whether we are already live? Because otherwise we will just wait for a few more seconds. Felix, can you maybe quickly check if the stream is live?
The stream is perfectly live.
Perfect. Also, on that point, thank you very much for our friends from Canada who are taking care of the recording and the streaming. I'm happy that more people can watch the OYPT finals because it will be very interesting. I've already shown you a slide in the very beginning. If you don't want to get recorded, please don't enable your camera. I mean, the teams are kind of have to, but everybody else, that's just how we're going to do it. All right. So my slides are a little bit Now it's much better. All right, to the OYPT finals. So the first thing that is different from the finals than from the pre-selected fights is that in the OYPT final, we will have the role of the reviewer. Now, for everyone who has IYPT experience, that is not a big, surprise. But for everybody who does not, the reviewer is a role that happens after the opposition, and it has the and it has the role of giving a short estimation of the presentations of the reporter and the opponent, and also to summarize the discussion and basically fill up any missing physics if there was any. And for that, we will have additional stage timings. We will have 3 minutes time for questions of the reviewer, which will happen after the opponent summarizes his or her discussion. Then we will have 4 minutes time for preparation of the reviewer, which is slightly longer at the OYPT. We will have 4 minutes time for the reviewer to take the floor and do their presentation. And then the 1 minute time for concluding remarks is moved, of course, after the reviewer. Now, as has been the case for the OYPT, we're a bit spontaneous. So I had to make the jury for the finals yesterday. And since, of course, all the time zones are different, I didn't get to talk to all of the jurors. Now, I've asked all of you in the jury, which is, let me just quickly give you the list of jurors, which is Felicia, Maria, Louis, Yaneshwaran, Sung, Yongyuan, Yonis, Yudong, Carrie, Mohammed, and Klim, whether you have experience with the review from your national competitions, because you haven't seen it at the OYPT yet. If you do not have experience with the review, I've asked you to tell me so that we can change up the jury. But nobody complained, so I hope that everybody knows what will be happening. But if not, then please type into the chat real quick, and we will have to figure it out. I'm sorry. All right, perfect. We will give them just a few more minutes. All right. Sounds good. If anybody continue on confirming, but I will continue on with the slides as well, because it doesn't seem that we need to change the review. The jury, sorry. That is great, because there would be a little bit of chaos. Good. An additional point at the OYPT finals grading is that the grading will be done in secret. That means that your grades will not be read out after each stage. Instead, you input your grades into the system. The fight assistant can see them. They will let the chair know that everybody has input them, and just send it in the private chat in the BBB room. Then the chair asks the jurors with the highest and lowest grade to justify, and also possibly other jurors to give some feedback if Felicia thinks that's a good idea. And jurors, please try to give feedback without revealing your grade. You should tell, of course, what you disliked, what you liked, and you will know whether you are in the lower or higher region, because Felicia will tell you before they ask you to give feedback. So that's how you know whether you should focus more on why you gave a rather low grade or a rather high grade, but please do not reveal your grade. And then the final result and the grades will be revealed during the closing award ceremony, which will happen just after the OYPT finals is done. As I already stated, the OYPT finals will be streamed. Thank you for the guys from Canada for this one. And anyone who does not want to be recorded, do not enable your camera. After the finals, and also during between the stages of the finals, we'll have 15 minutes break. And then we will have the closing ceremony, which will just happen in this room. Or Felix, if that's not true, then you just correct me, which will happen somewhere. And then it will also get streamed. So, and then then we will have the award ceremony. Perfect. It will be in this room. Thank you very much. That leaves me with wishing you good luck and to have fun at the OYPT finals. I think we have all our jurors here, so I will check real quick again. So Felicia doesn't have to. Felicia is here. Maria is here. Is Maria here?
Yes, I am.
Perfect. Sorry, I need to scroll all the way down. Good. Then we have Mohammed, Gyaneshwaran, Havi, Sungyu. I've seen him. Yongyuan, Yonis, Yudong, Karim, and Klim. I haven't seen you before, but now you're here. Klim, though, you're currently not in the audio. Now you're back. Klim, you're good to go? I mean, he's joined in the audio, so if he has problems, he will complain. And if he does have problems, we will just exclude his grade, but seems to be good now. All right, then. Felicia, thank you for taking over, and good luck.
Right. Thank you. So welcome to the final of the OYPT. And we have the three teams of Singapore, Germany, and Austria here. And it'll be a very, very exciting 3 rounds of the final. So we have reporters, opponents, and reviewers in the final, as you're all aware by now. So I would like to start by having the jury introduce themselves, and then I will ask the team captains of each of the 3 teams to introduce your teams before moving on to preparing for the fight. Okay, great. So if I could have all of the jurors, please turn on your cameras, and I will ask you to introduce yourself. So my name is Felicia. I was part of the Swedish team in 2010. And then thanks to OYPT, I ended up moving to New Zealand for my PhD in condensed matter physics. And now I work for a startup working on climate change. And all right, let's go through the long list of fantastic jurors. So could I ask Luis to please introduce yourself?
Okay, hi, my name is Luis Henrique. I'm from Brazil. I graduated in physics in São Paulo's University. I'm a teacher and I work with the Brazilian team in the OYPT. It's my first time as a juror, and good fight to both teams and all teams here.
Thank you. And we have Yaneshwaran.
Hello, I'm Janeshwaran from the Doon School, Dehradun, India. I've been associated with IYPT for the past 3 years. I've been guiding my students to qualify for Team India, and this year 2 of them qualified. And this is my first year as jury. Thank you.
Thank you. Sung Yu.
Hello, I'm Sung Ju Hong from Gangwon National University of South Korea. Actually, this is my first time to attend OYPT as a juror. Also, it's very honor for me to attend a final stage as well. I enjoyed the whole tournament, and I hope that final team enjoy everything. Thank you very much.
Right, thank you. We have Young Won.
I'm Yongyuan Shu from Taiwan. I personally involved into IYPT for 14 years or so. So I hope that everybody can enjoy the fight today. Thank you.
Thank you. And we have Ioannis.
Hello everyone, I am Ioannis Kalantzis. I'm an independent juror from Greece. I got my bachelor's degree a few years back, and now I have my master's in physics didactics and educational physics, and working as a physics tutor for the past couple of years. Hope everyone has a good fight, and may the better team win.
All right, thank you. Carrie.
Kia ora, my name's Kerry Parker. I'm, I should say good evening. Michael said good morning because it's evening here in New Zealand. I'm in New Plymouth, where I'm a high school physics teacher. Been involved with IYPT for a long, long time, and also the New Zealand team. And I'm feeling really looking forward to this final. Last year I was in Romania. Turns out I had COVID while I was being a jurist. So afterwards I tested positive. So I'm feeling much better this year. I'm looking forward to a really great fight. Good luck to all 3 teams.
Great, thank you. Mohammed?
Hello everyone, I'm Mohammed. I'm a PhD student in aerospace engineering in Iran, and I've been in this competition for about 10 years now, and I hope you all enjoy the fight.
Right, thank you. And we have Klim.
Klim's just trying to fix his mic.
Ah, right. Okay. We will. We'll get Maria. In that case.
Hello, I'm Maria. I once was also a participant in the Swedish IYPT 2012. And since then, I've been involved as team leader and now juror. I've studied engineering physics, and now I'm studying to become a teacher.
And Clem has posted in the chat that he was a participant of the AYPT in 2011, 2012, and now have 102 tournaments behind him. That seems like a lot. Excellent. So it looks like we have a lot of physics experience, a lot of physics teachers, a lot of previous participants. So it's great to have you all on the jury panel for this final. And now I would like to ask the team captains of each team to please introduce their whole team. So if we could start with the team of Singapore, please.
Okay. Hello everyone. I'm Luke Mazuru, the team captain of Team Singapore. On my right are Martin and Inze, and this is Hilary and Jinxiang. Over there is Penny the penguin, our team mascot, and this is Mark the monkey, also our team mascot. We look forward to having a very good physics fight. Thanks.
Great. Thank you very much. Team of Germany, please.
Hi, we're Team Germany. I'm here in the front. I'm Louis Liebenstein. I'm the team captain. Next to me is Luan Sliva. We have Florian Bauer, Tarek Becic, and Maya Lütke. And not forget our team mascot, Horst. And before we start, we would like also to thank the Swedes for organizing our great trip and the meetup here in Sweden, which we really enjoyed. And we also look forward to a great physics fight. Thanks.
All right, thank you. And finally, the team of Austria.
Hello everyone, I'm Elias Koshir from Team Austria, and we're right in the room above Team Germany in Sweden. This is Markus Pfeiffer, this is Johannes Schmidt, Jeremias Costa, and Anisa Asikulova. And we're looking forward to an interesting physics fight.
Right, thank you very much. So that's all of the initial setup pleasantries sorted. So for the first fight, we have the team of Austria reporting problem number 17, arrest or bid, and team of Germany opposing, and team of Singapore in the role of reviewer. So what are we doing for time? We're doing the 5-minute preparation as normal? I'm assuming, yes? Great, okay, cool. So in that case, team of Austria, you have 5 minutes to prepare.
May I just have the presenter rights?
Yes, definitely.
Could you let me know what laptop you want to have the presenter rights, please?
The one from Markus Pfeiffer, so my own laptop, the one I'm talking on.
You all sorted for starting? Looks like maybe Team Austria are having some technical problems.
Am I now clearly audible? Since I just had to set up this multi-monitor setup, and then I was unmuted, unfortunately.
Yep, no, it's I can hear you very clearly.
Okay. Then yeah.
All right, are you ready to start?
Yes, I'm ready to start. So welcome
Excellent.
to my presentation. Welcome to my presentation on problem number 17, arrestor bed. So first I'm going to read out the problem statement. So a sand-filled lane results in the dissipation of the kinetic energy of a moving vehicle. What length is necessary for such an arrestor bed to entirely stop a passively moving object, so example a ball, and what parameters does this length depend on? So in this phenomenon demonstration, we can see that the entire kinetic energy of the sphere gets absorbed by the granular material. So there are two main energy dissipation mechanisms. So first, the sphere has to push sand in its path upwards against gravity and piles it up along its path. And then second, the sphere has to compress sand in its path in the bottom region, and this requires deformation energy. And then there are also like other losses, for example, like air resistance or friction of the individual grains of the granular material. And these frictions lead to heat losses, but those losses are neglected. So then we can so with this we can then formulate an equation for the braking distance in the x direction, which is just the entire energy, so the derivative of the entire energy from the sphere with respect to the x direction, and so with respect to x. And if we then take a look at at an infinitesimal step into this x direction, we can then calculate the force only from the displacement of sand. And we can calculate this braking force only from the displacement of sand by multiplying this area where sand is getting displaced from times the density of sand times the gravitational constant, and then times the height which this sand gets elevated. We can also then formulate an equation for the braking force from the compression of sand, which is just the area of sand getting compressed, times the compressibility of sand, which we will go into detail later. And as I've already stated, these other losses are neglected. When we then further analyze this and type in some common values we see, we can thereby calculate this entire energy from the displacement of sand, and also calculate the velocity of, so the energy from the ball upon entering the arrestor bed. And we can see that the energy from the displacement of sand makes up only about 1% of the entire energy from the sphere. So also this displacement mechanism can be neglected to further simplify our model. So we are left with this compression energy, and the question now is, what is this compression energy? So when the sphere rolls over the granular, this loose granular material, this loose granular material interlocks, and the sphere has to push against these interlockings, and thereby then can rearrange this granular material. So these interlockings exert normal forces from the granular material to the sphere, and the sphere has to push against these normal forces, requiring energy and thereby slowing the sphere down. Now we have to do a lot of measurements. So we can first formulate an equation giving us the braking distance with respect to this braking force from the compression of the granular material. Therefore, we need this area where sand is getting compressed, and this we can get this by getting the area where sand is getting this total area where sand is getting removed from, which is the purple one, minus the area where sand is getting piled up. We can measure both of them when we measure the profile with our robot. And then we also need to get this compressibility. And to get this compressibility, we have to we take loose granular material, place a coin on top of it, then measure the distance from a reference point to the top of the coin, then place some weights on top of the coin so the coin sinks in, and then we measure the distance again. So that allows us to calculate the volume that was getting compressed, which is just the area, the surface area of the coin times the delta H. And then we also know what energy was required for this compression, because it's just the change in potential energy of these weights we applied. Here you can see these measurement results, and only this green highlighted section in the left graph is relevant for us, for our arrestor bed. And we have also cross-checked this with literature. So in the right plot, this green area corresponds to our measurements, and that allows us to determine the compressibility for our granular material, which is around 11,000 Pascal. Next, we can measure the profile. So we have a slope within our setup. We have a slope to accelerate our sphere. And once this sphere has completely slowed down, we can then use our distance ranging sensor to take this to map the entire arrestor bed in a grid of 1 by 1 millimeter. And here you can see some measurement results. And as you can see, we have a very high resolution, giving us a lot of detail, which we can then use for further examination. So if we now divide these the entire path of the sphere into sections of 20 millimeter and average the cross-section, we can see that this cross-section remains constant along the x direction, so the rolling direction of the sphere. So we have a constant sinking depth here in orange, and also a constant cross-section. According to our theory, we can then formulate a hypothesis that with this constant profile along the x direction, we have a constant compression force acting on the sphere, and thereby we have also a constant deceleration. So to verify this, we have this video tracking setup where I've placed my smartphone with the slow motion settings above the arrestor bed, and I've also need to keep my LED from the smartphone on because that allows me to use my custom tracking algorithm, which tracks the bright reflection spot on the top of the sphere, allowing me to do some very accurate video tracking of the sphere. Here you can see one of these tracking results, and as you can see in the rightmost graph, the velocity of the sphere linearly decreases, and this linear decrease means there's a constant deceleration and thereby also a constant braking force, which is exactly what our model predicts. Next, we go back to these cross sections, and if we compare the cross sections from different experiments where we altered the impact velocity from the sphere, we can see that also the cross sections remain constant, and also the sinking depth remains constant for different initial velocities. We can also see that the ratio between the area which is getting compressed to the total area where sand is getting removed from remains independent of the initial velocity. And then we can do a lot of parameter variation for our experiments. So we change the sphere diameter, the sphere mass, and also the initial velocity of the sphere. There we have a lot of experiments, and therefore we help ourselves with automation. So I've built this robot which automatically measures the distance the ball, so the breaking distance, and it repeats my experiments, helping me a lot. I've also then used for the diameter variation and mass variation 3D printed spheres, because this allows me to independently vary diameter and mass, because in my slicer program I can change the infill of the sphere. And then we can analyze the effect of the diameter. So we can see that with a larger diameter, we also have a larger breaking distance. This is because with a larger diameter and a constant mass, we don't sink in as deep. With this sphere doesn't sink in as deep, and thereby there's also a lower compression force acting on the sphere, and thereby also a lower breaking force, resulting in a larger breaking distance. Rather similar effect we've got with the mass. So with when increasing the mass, we have a larger sinking depth, and with this larger sinking depth, we have a larger compression force, and a larger force from this compression, and this larger breaking force then results also in a smaller breaking distance, as we can see from our measurements. And finally, we can also then have a direct comparison here, for example, in this plot where we altered the impact velocity of the sphere. So in red, we have our theory, and the blue points are the data points for different impact velocities of the sphere. And we can see that our model fits these data points. So as we increase the impact velocity, we also have a larger kinetic energy of the sphere, which also results in a larger breaking distance. And this is also modeled by our theory. And the red area accounts for the measurement errors in the compressibility of the granular material. So we estimate with around a 30% insecurity. And when taking this into account, we can say that all the data points are within our confidential interval of our theory, and the theory models our data points. So to conclude, I've done some highly detailed measurements of the sand profile with a great resolution. So then I also used automation to help me with my experiments and also keep them reproducible. I've done an in-depth analysis of the parameter dependence, also using these 3D profiles. And then I've also compared my theory with my experiments and seen some very good agreement. So thank you for your attention.
Thank you. Now we have the team of Germany in the opponent roles. You have a few minutes for clarifying questions.
Yes, my first question would be to your experimental setup. How did you ensure the same initial conditions for the compression of sand for each measurement?
Yes, so for example, this is how I prepared my arrestor beds. So I've realized that, for example, shaking the arrestor bed to really have
Please a short answer.
Okay, so shaking the arrestor bed is not a very good idea, because this would change this would have a higher density of the granular material, since it already fills up these air gaps in between. So I used a tool like the one you can see here on the screen.
Okay, thanks. I think that answers my question pretty well. Thank you. How did you ensure a smooth surface for the 3D printed balls? Because it seemed like the surface was quite rough.
So I used a sandpaper to ensure that this is as smooth as possible.
Okay. Then I'd like to ask you. You stated that your energy, that you have a lot of kinetic energy when the ball comes down your round, which I agree with. However, not all energy is dissipated into translational, but also rotational energy. So did you consider any sort of angular momentum in your theoretical approaches?
So my theoretical approach only focuses on this displacement and mainly this compactation of granular material. So for my theoretical approach, this consideration is not that relevant. So I've stick to
thanks. In the beginning, you made an assumption that the potential energy is neglectable and the sinking depth is neglectable in your case. Is that assumption true for all if you change initial conditions, for example, the mass of the ball drastically?
Yes, this remained this assumption remained true for all my experiments which I conducted.
Thank you very much. I think time is over. We go into preparation.
Right. You have 5 minutes to prepare for your opposition.
Could the opponent please let me know what laptop they would like to have presenter rights?
It would be this one here, please, with the account of Louis Liebenstein. Thank you. Okay, so I'll start with the opposition presentation. Thank you very much for your nice presentation, first of all. So to the report itself, we thought that you had a very good basic explanation and showed three different types of energy losses, and also had a very sophisticated science communication with helpful visualization at all points. You basically looked at the displacement of the sand to the sides, but you neglected the dissipation of energy to the front of dampening, which is very different behavior than to the sides. And some aspects of the task were not fully fulfilled. For example, you only used balls, no other shapes, which is not especially specified. And also there was no proof why the friction is neglected. So with heavier balls, we would think that this is very different. You also had very rough balls at some points, in which, well, with less smooth balls, this influence is quite bigger. And you also neglected the sinking of the ball, which we believe is actually pretty predominant, especially in the cases of heavier balls. Going on to the experiments, you had a very sophisticated robot to measure the surface of the lane, which we quite enjoyed. You did some independent measurements of the compressibility of sand, which is very nice, but the measurements were sometimes quite questionable. For example, no error bus and sometimes very strong deviation. For the parameter variation, you did some variations, for example, the initial velocity, the object density, and the size. However, you did not vary the sand compression, the humidity, which has some effect, of course, on the weight of the sand, the sand height, and also, which we discussed earlier, the shape of the object. You used you only used 3D printed balls with a constant infill, which is very sophisticated to vary the mass independently. However, that leads to error because of an impact of an imperfect surface, as we've clearly seen in pictures of yours. At the same time, it was unclear how the energy of the ball was calculated. In this case, it's very, very important that the energy splits throughout through translational and rotational energy, which you completely neglected in your calculations. The friction and the transition from the red into the sand were also quite heavily neglected. And also your error analysis was lacking to some extent. Your error bars were partly given but not explained. Yes, to go on to the theory itself, you base your theory on three different kinds of energy dissipation, which was quite nicely explained. We have the displacement of sand, which is neglectable in your opinion, which we don't fully agree with. You have the compression of sand, many sources of energy loss, and the friction, which you neglected, which we agree to a certain extent. You gave a very simple approach of these three phenomena, but as I said, two were neglected for quantitative modeling, and that was only partially justified. To the comparison between theory and experiments, you did a good comparison, but they had sometimes significant deviations, which we will discuss in the later discussion. Also, you did not include the rolling of the ball, the angular momentum, as previously stated, the sinking of the ball to a certain extent, and the sand displacement in front of the ball, which is, for example, dependent on the lane width. And we believe that for heavy objects, this is quite important. And there was no explanation why the friction was actually neglected, which could be easily included which could have easily included in your theory. So overall, we believe that you did investigate the phenomenon to a certain extent. However, the dissipation of kinetic energy was only investigated to a certain extent, not including the rotational kinetic energy. You did observe a moving object, but you did not vary all the parameters that we would like to see, and thus we think that the task was mostly fulfilled, but it had some important lacks. Thank you very much. So we can continue to the discussion, I believe. If you'd please open your presentation. Probably need presenter rights for that.
Yes, I do need presenter rights.
Okay. So maybe beginning with your experimental setup, I'd like to talk with you about majorly the balls that you used for your experimental setup.
Okay, yeah.
If you could go to that slide, please, where you showed your different spheres.
The 3D printed ones, or?
Yeah, the 3D printed ones, please.
Yes.
So I believe it's quite nice that you use 3D printed balls. However, I believe that there's a certain error that can be happening due to the roughness of the surface, and that is especially concerning because you neglected any kind of friction alongside the ramp in your experimental, in your theoretical approach. So how did you actually ensure that this ball had a smooth surface and did not change the symmetry of the ball with like sandpaper or anything?
Yeah, so since I hadn't got some advanced tooling, I had to use sandpaper and had to do this by hand. However, when I just tested the spheres rolling normally, then I realized, so on a solid surface, I realized that there is not a very major impact from these small small deviations in the surface. So I think it's so I think the usage of 3D printed spheres is appropriate for this experimental setup.
I would agree to a certain extent. For example, the roughness of the surface can't really be controlled very accurately by hand. I would have probably used some sort of chemical smoothing instead of like mechanical smoothing via sandpaper. And also, you do have a certain limit of masses for the balls. If I could ask you pretty straight up front, what was the heaviest ball you used in your experiments?
I haven't got the data right here. For the, I can only say for the, for example, the larger metal ball, it's 28 grams. And as far as I know, the heaviest 3D printed sphere is slightly below this weight.
Okay.
But
I think that's enough.
I just
I think
wanted to add.
Yeah.
Okay.
Okay. Yeah, so I believe that this is actually well, I think it was lacking some parameter variations in that sort of sense. I mean, you did vary the mass, which we enjoyed, but at the same time, you do have a certain limit which you cannot overcome. And I would love to see actually heavier balls in that setup. For example, three like metal balls or anything. But maybe to move on a bit.
May I just add that I've used metal balls, as you can see, for example, for this custom tracking algorithm, and smooth metal ball was necessary for the reflection, and I also used them here in this experimental setup. So because, as you say, there may be some difficulties with the surface of 3D prints, which can to some extent be neglected, but to really ensure this, I also use these metal spheres on a metal slope to really have the lowest friction. Yeah.
Okay. So maybe in that case, I'd like to add that the simplification you've done by neglecting the friction and the energy dissipation through basically the hill in front of the ball only really applies to the metal ball in that case, not really to 3D printed balls. And I'd like to see I'd love to see that assumption matches with the other balls as well. But maybe going on to your theoretical approach, you stated that you neglected friction and the energy dissipation into potential energy from the hill that basically forms in front of the ball. Maybe in that case, it would have been important to actually consider any case of rolling in your energy calculations. Did you consider rolling in any sort of that energy, or did you only consider the kinetic energy into translational kinetic energy?
I mainly focused on this translational kinetic energy because it really is the majority of the phenomenon. And as we have seen in our comparison between our model and our theory, this also follows accurately the data points which we measured. And therefore, I didn't see it necessary to really have a more complicated theory for less gains, which this would give us. So I stuck to this translational kinetic motion of the sphere. And also, the balls are not very large, so it shouldn't. So this rotational energy isn't really isn't too big.
Okay, so maybe following up on that, could you go to your theory experiment comparison?
Yes, I can.
So what I believe you can see in that graph here is that while you do have a certain progression that your theory predicts and that your experimental data seems to follow, but you do have some quite large deviations in there without error bus by the way, which I just now saw. But that doesn't really seem to follow your theoretical approach is quite nicely. And I do believe that this could be a source of the rotational energy, which you completely neglected, especially with heavier balls at that sense.
Should I just elaborate on this error, or because
could you...
So as we can see, this all these data points are within the area of this compressibility of the granular material, and as you have already pointed out, it is really challenging to maintain comparable compressibility of this granular material, which I've really tried hard to leave this one constant with also this tooling, which I have. And like, of course, and at some point the granular material settles, or for example, also shaking would mean settlement of the granular material and thereby also a higher density of this granular material, thereby also impacting this the breaking distance. And when really taking all these things into consideration, I would say that for a granular material experiment, all my my theory really matches well the data points which I gathered. And all these data points are also within the range of the error from measuring the compressibility.
Yeah, well, I wouldn't quite agree. I think that in this case, the rotational energy is not to be neglected, and that the energy itself has a deviation of a certain factor, because of course the moment of inertia for a ball cannot be neglected in that sense, because it is a rolling of the ball, which is stated in the task specifically, and I do believe that you have not actually investigated that phenomenon of the rolling quite as much, but maybe going on, have you investigated other shapes than that of a ball? For example, a hollow cylinder or a solid cylinder rolling down the inclined plane.
No, I've stuck to this ball. I would also like to know what you would expect different for like different shapes, because I would say that there's not really a lot of gain when switching to a cylinder. Also,
I would actually
decreases.
Yeah, I would actually disagree with that. I believe that, as I stated previously, the rotational energy is quite important in that case. And because the moment of inertia for a cylinder, a hollow cylinder, and a sphere is quite different, I actually believe that that is a lot of difference in there. But I think that concludes our discussion. And thank you very much. I think I now have time for the concluding remarks. So first of all, in the discussion, we talked about the experimental setup of yours and the parameter variation. We talked about the 3D printed balls you used, and we think that there's an error due to the rough surface, which you could have handled through chemical appliance, for example, and that there's also a limit for the mass of the balls, which you haven't investigated, for example, any heavier balls, and thus the friction neglection only is valid for your metal ball and not for the actual balls used in your experimental setup. Then we talked about the theory and the rolling energy. We do believe that there's a deviation from the theory we saw on your theory experimental slide, and that we believe that this is because of the neglection of rotational energy, and thus the moment of inertia also that needs to be heavily considered in the theory. And also we talked about shapes of the object and the moment of inertia, which is quite different throughout those objects. And we believe that you could have investigated these cases more nicely to fulfill the task more nicely. But we think that the discussion was quite nicely, and I thank you very much for that.
Thank you. All right, we move on to questions from the reviewer. You've got 3 minutes.
Sorry, could the reporter please share his slides?
Yeah, yes, we can get that sorted first.
Thank you. Right, may I begin?
Yes, yes.
Thank you. Thank you both for the very insightful discussion. Could the reporter please go to slide number 26? Are both of these graphs experimental or theoretical?
Those are both of these graphs are experimental.
Right, and how many data points do you take for the graph on the left?
For the left one, it's like for each color you have like 30 to 40 data points.
Okay, thank you. And to the opponent, what do you believe the main source of energy dissipation is in the system?
I believe that...
Sorry, to the opponent.
To the opponent, yeah. I believe that the main source of energy dissipation is actually the resisting energy of the sand itself, which basically forms throughout the hill in front of the ball. And I do not believe that the compression itself is actually, well, I mean, it is valid, but only for lighter balls. And I believe
So you
that
believe the main cause of energy dissipation is the sand being accumulated in front of the ball?
Yeah, I believe so.
Okay, thank you. To the reporter, did you ensure the particle packing ratio was the same before each experiment?
Yes. Yes, I did.
Okay, thank you. Does your theoretical model account for the build-up of sand in front of the ball?
So the theoretical model models this sand in front of the ball because this, so indirectly, since the sand in front of the ball also gets pushed to the sides as we observed, and since this requires energy to, so
right, okay,
in the end
thank you. Sorry for interrupting, but thank you. To the opponent, do you believe the particle packing ratio is an important parameter in the system?
Yeah, I believe so.
Okay.
I think the energy yeah.
And do you also believe the grain shape is an important parameter, like the particle shape?
Yeah, to a certain extent, I'd say so. But more the particle size instead of the particle geometry itself, I believe.
To the opponent, did you assume the particles were spherical? And if you did you verify this experimentally? Oh, sorry, to the reporter.
So the particles we used, they were not spheres. They were like regular sand you have, which is has sharper edges, and so
then that's fine. But did you ensure they were the same size?
Yes, they are the same size. So they're constant. So in this constant range, and they're like granular material, which you would regularly find.
Could you
so
go to slide number 1? Oh, sorry, slide number 3.
Slide number 3.
Yes. As you can see, there are some larger grains on top of the bed. So would you still believe that they are of constant radius?
So I would say that they're still within a extent which is good for the experiment. So this maybe some imperfections in the granular shape in the size of the granular material. There was no major impact, or there was no impact on the experiments. So there may be
I'm gonna have to interrupt you there. You're past your time. We're gonna move on to preparation of the reviewer. That's 4 minutes.
Hi, could I have screen sharing permissions? Okay, thank
Yep, doing it now.
Sorry, I think we got screen sharing pumps on the wrong account. It should be to Luke Maziru.
Okay, he should have them now.
Oh, bisexual. Right, can you see my slides?
Yep, I think they're coming. Yep.
Right, thank you. May I begin?
Go ahead. Yep.
Alright. Hi everyone, I am Martin Ko from Singapore and today I'll be reviewing problem number 17, arrestor bid. So we will firstly begin with the report. For the strength of the reporter has qualitatively discussed various mechanisms of energy dissipation, like the compression of sand, displacement of sand, and friction. They have then experimentally measured the sand profile using a robot, and this allows us to accurately investigate the depth of the groove formed. There was also an automated release mechanism, allowing the reporter to take a large amount of data, and he has also characterized compressibility experimentally and leveled the sand bed after each run. However, there are some areas for improvement within the report. Firstly, there was a lack of comparison between theory and experiment for numerous graphs shown, and in specific, it refers to the graphs of the effect of mass and diameter on the motion of the ball, and this shows there is no demonstration of predictive power into the model. There was also a lack of relevant parameters investigated, like the packing ratio, shape and size of grain, depth of bed, and the geometry of the object. Next, there was poor experimental control, and the sand grains were not constant radius, as can be seen from the reporter's slides, and a possible way to address this would be to use a sieve to sieve up particles of similar radii. There was also an unsmooth transition from the ramp to the arrestor bed, resulting in energy loss upon collision, and this will also affect the sinkage depth of the ball upon collision with the sand bed. The reporter's quantitative model fails to account for the following. Firstly, the rotational kinetic energy of the ball. Secondly, the piling up of sand in front of the ball, and I believe that this is significant, and it will also inhibit the ball's motion since more sand blocks its motion. Thirdly, it doesn't account for friction, and these possible reasons could account for the deviation for the velocity against distance graph. Lastly, the reporter has assumed the packing ratio remains the same throughout the bed. So now onto the opposition. For the strength of the opposition, he has rightly pointed out many relevant points, like the lack of consideration of friction, the sinking of the ball, the lack of consideration of rotational kinetic energy, and the lack of parameter variation, like the packing ratio and the depth of the bed. However, some areas for improvement include the fact that the opponent has not pointed out some relevant points, like the lack of theory experimental comparison, the lack of investigation into some relevant parameters, and poor experimental control. A trivial point was raised regarding the 3D printed ball, which I would like to discuss later. Lastly, the opponent also believes that the sand in front of the object, the sand being built up in front of the object, is a major source of energy loss, and I believe the reporter has demonstrated that it is negligible, and I believe that compression and friction is the main source of energy dissipation. So now I'll move on to the discussion analysis. Firstly, there was a discussion regarding the use of 3D printed balls, and I agree with the reporter as he has made an attempt to smooth the balls to smooth the surfaces of the balls with sandpaper, and by using 3D printed balls, it is easy for the reporter to vary the mass and the diameter of the ball, which are some relevant parameters in this system. Next, there was a discussion about the small experimental range regarding the mass of the balls the reporter has used, and I partially agree with the reporter in the sense that he has investigated heavy metal balls, and I believe that he should have discussed the effect of these balls and how they will result in a greater accumulation of sand in front of the ball, and how sinking will be more significant for heavier balls. Next, the next discussion point was regarding the lack of consideration of rotational kinetic energy. And the opponent felt that rotational kinetic energy should have been considered, while the reporter felt that translational kinetic energy should have been considered. And I partially agree with the opponent, as rotational kinetic energy would be the same order of magnitude as translational kinetic energy. However, I disagree in the sense that the opponent feels that this is a possible source of overprediction in his data, but I believe that this will result in an underprediction. And next, there was a discussion about the object shape, and I agree with the opponent as the moment of inertia and contact area will be affected. So for my final verdict, I believe that the reporter has given the qualitative reasoning behind the energy loss through compression, but there was no direct answer to the problem statement regarding the effect of relevant parameters like the packing ratio and the grain shape on the distance traveled by the object. And the opponent rightly pointed out the lack of consideration of friction or plowing of sand, but missed some key points regarding experimental control and the parameters. Thank you.
Thank you. Right, we have final stage, which is the closing remarks of the reporter. We'll get your screen sharing up.
Wait a minute. Who needs the presentation?
Please give presentation rights.
I have it.
Okay.
I have it.
Okay. Just 1 second.
Yep.
Den Computer einfach dafür zu.
So, first I would like to thank the opponent and the reviewer for the discussion and their extensive feedback. So I just wanted to mention that this hill forming in front of the ball is only the cause for this compression and this displacement of sand, since the sand in front of the ball gets pushed to the side or below the sphere. So this hill forming in front, which was mentioned, is indirectly accounted by my theory. Then also this friction is negligible because we realized that this initial potential energy of the sphere, which it had on top of the ramp, was equivalent to the compression energy. So all these energies which we observed were experimentally measured. So the this potential energy from the sand was also obtained from my 3D maps, where I have got 30,000 data points each, and it's considered negligible. And this and the compression, yeah, and also we consider this compression there as the most important parameter. So I would thank you. So thank you for that.
All right, thank you very much, all three teams. We'll move on to questions from the jury. If you'd like to ask a question, just raise your hand in the with the raise hand button. Yes, Maria, do you want to start?
Sure. Reviewer, I have a question for you. In your review speech, you said that the opponent focused too much on, or the opponent answered that if there's a pile of sand in front, like that's and that was important, and you thought that that wasn't important, and that the reporter justified that. But then in your summary, you said that the reporter missed that part of the problem. So, what is your opinion? Is the pile of sand in front of the ball relevant or not?
I will agree that it isn't important since the gravitational potential energy gained by the hail isn't very significant. But I believe that the discussion regarding this aspect could have been better by the reporter, and I didn't feel it was very clear as to why this was negligible.
Okay, Ganeshwaran?
My question is to the reporter first. So, reporter, you had shown a graph of braking distance versus impact velocity, and the experimental data were shown in the form of a single point for each impact velocity. So, do I assume that you did only one trial for each impact velocity and got the graph, or did you conduct multiple trials?
So here, yes, you're right. In this one particular plot, afterwards, I've also done this object tracking, which also aligns with my theory. But in the graph you have seen, you really see these single data points.
So actually, if you have done multiple trials, like 5 trials for each impact velocity, you must have you might have seen wide variation in the stopping distance. So that would have given you some error bars from experimental data, which you can compare with the error bars from theoretical data. So without the error bar of experimental data, it's not very good to compare with theory. Do you agree?
I agree that error bars would be a great improvement, and I will implement this in my later works.
I have a question for the opponent. Can I ask?
Sure, yeah, go ahead.
Opponent, you mentioned about the reporter not accounting for friction. Now, for a ball rolling on sand, do you think friction is involved? Because friction only helps it to roll forward. So, is it friction or rather rolling resistance which plays a role?
Well, I believe that friction is not as important as the rotational energy itself, and I believe it should have been considered. But the most important point in this sort of sense was actually the the rotational energy for me, and I believe that his theory is actually off by a factor of 7/5, which would have been the accountants for the rotational energy in that sense, and I believe that that is a quite big error actually in his theoretical approach.
Same question to the reporter. Do you think friction plays a role? Like, as long as the ball is rolling on the sand, it's rolling without sliding. So, doesn't it eliminate static friction from the picture as well as kinetic friction because there is no slipping? It's just rolling. So, does friction have any role in the
Can you
theory?
repeat your question? It's acoustically, I have problems understanding it. So you were talking about whether the ball is rolling or sliding. Am I correct?
Yes, as in all the videos, in all the data points, the ball is clearly rolling and then slowing down and coming to rest. It's not sliding on the sand. So if it is rolling, Don't you think there is no static friction and there is no kinetic friction which is going to play a role in the motion? It's just rolling. It's not sliding.
Yeah. Yeah, the ball rolls and there's some degree of slippage, but yes, the ball is rolling on this arrestor bed.
So then the reporter's
Okay,
theory
okay.
of
I think we should move on to another juror. I've got some more who would like to ask questions. Thank you. Ioannis?
Yeah, a question for the reporter. Can you go to slide 25, please?
Yes,
Yeah.
I can. I just have to get the presentation up. 25, you said?
Yes, slide 25. On the graph on the left, you can see that for a specific diameter of a ball, you have a difference between 200 and about 300 something. That's your limit of your measurements, correct? For example, for the 25 millimeters, if I'm seeing the graph correctly, yes?
Yes.
Yeah. How can you explain this relatively big difference in measurements across this whole experimentation?
So since I've done many measurements, there are of course some outliers. There will always, due to the high number of experiments, occur some errors in the or some imperfections in the experimental setup. Like you have to really be careful with the granular material. So with that number of measurements, there of course will at some point be some outliers.
Okay, thank you very much. Thank you.
Right, that's the end of questions from the jury. We will move on to grading. Nominally, there's 5 minutes for grading, but we'll take the time we need until everybody's done. So see you back here soon for motivating your grades. All right. We have grades come in from all of the jurors. And I don't know what the grades are. We will see that at the closing ceremony. But I'm going to ask some of the lows and highs for all the three competing teams to justify their marks without saying what the mark is, to keep the suspense for the closing ceremony. So we'll start with the reporter. So Maria, you're one of the lows. Would you mind giving some feedback to the reporter?
Yeah, sure. I appreciate the experimental work you put in, but I do think like the lack of error bars, how do you say, like it's unclear whether some of your experiments which would need repeating have been repeated. For example, the compressibility, and then also the lack of including like rolling kinetic energy into the theory, I think is a bit problematic. So that's probably why I ended up on the lower end.
Cool. I'd also like to ask Carrie to comment on the reporter for the log.
Hang on, I'm here. Yeah, I was concerned about the sort of assumption that the gaining gravitational potential energy of the sand was all the sand was, you were lifting it up or recompacting it. I think there's a lot more going on with sand grains moving around a whole lot. You can see that in the videos, and it was just not looked into. Like Maria, I was super impressed with your robots and the measurements, but it just wasn't doing it for me for in terms of the theory, the rotational kinetic energy being ignored and just some really very bland assumptions being made. I felt just left it wide open. Yeah, just saying that the kinetic energy, translational kinetic energy was most important because I didn't really see how that was being justified. There was some really awesome experimental work, but I just didn't feel that in the final the theory was backing it up. The assumptions were just too simplistic.
Okay, thank you. And for the highs, we have Gyaneshwaran. Would you mind commenting on the high?
I was actually super impressed by the way they have collected the data and presented it on slides in the form of graphs, and they've taken pains to do the 3D printing of the balls and to vary the mass without changing the diameter, because that's an interesting thing to do. Usually when you change the mass of a ball, its diameter also increases. So they have eliminated that and ensured that it was controlled. So the graphs they generated out of this experiment was pretty illuminating. So they have done some good work. So that's why again.
Cool, thank you. And for the opponent, one of the low scoring jurors is Carrie. If you wouldn't mind commenting there again.
Me again, sorry. Hang on. Yeah, I was concerned about this idea that there's a resisting energy of the sand is less important than the rotational energy. So it just seemed to, I mean, the questions you asked, you got a good score for that, and the opposition speech was quite good. But in the discussion, it was all about whether you'd sanded down the balls, and if I'd had more time, we would have asked you what chemical you would have used to smooth the balls, because I thought that was like, I mean, there's 3D printed balls. How would you smooth them chemically? Maybe you know something. But and the idea that that there's a resisting energy in the sand, it was really not explained. The whole and the sand in front, the sand being lifted, you could have gone a long way in asking them about that. And this friction, I mean, what's friction? It really should have been unpicked a lot more. So So I gave you good score for the questions, good score for your, quite a good score for your opposition, but then the discussion started to go down a bit and I dropped you some marks in the questions, the reviewer's question, because I felt you seemed to be muddling energy with forces. So that was my score.
Thank you. And for the
Which you
one of the
won't know.
highs for the opponent. Now we're not going to say any numbers. And high for the opponent, Clip. Would you mind commenting on your high score?
I hope it works now.
Yes, it does.
All right. So I really like the speech, and according to grade sheet, is one of the most important things to do. And I understood what you mean about chemical smoothing the balls, and I put not really high marks for the discussion, same as Kerry. I've seen a really good speech, and probably that's why I think it was a great speech, because I heard a lot of things I mentioned in the report. Something like so it was a great balance between pros and cons in that speech. I agreed on basic explanation, but I've seen in the speech that assumptions were not justified by any arguments. So I agreed mostly in the speech, and then discussion was not that bad to lower the mark greatly.
Okay, thank you. And finally, for the reviewer, one of the lower scores is from Young One.
Okay. I think you can hear me.
Yes.
Actually, I don't think I'm giving a low grade. I think okay. The speaker, the opponent tried to review everything, so they speak in a relatively high speed speaking. Okay, so actually, in the question they ask, I give a pretty nice score, and for the review of the report and to the opposition, it's a little bit above the average.
Okay. Thank you for that. And then finally, one of the higher marks for the reviewer, Mohammed, would you like to comment?
Yes, thank you. I see the review very good. Questions was pretty precise. The review of the report, the review of the opposition was fulfilled, and the analysis of discussion was pretty good too. Maybe he forgot to mention a little of the missed points, so I think the review was very good.
Okay, thank you. And thank you to all the teams for the physics fight. And we will be back here after a 10-minute break. So it's currently 34 minutes past whatever your local time zone is, assuming you're on a whole time zone. So if you can come back here at 44 minutes past your local hour time zone, that would be great. And for the next fight, we will have team of Germany presenting and Singapore opposing and Austria reviewing. So see you back shortly. Could I ask that the jurors and teams, when you're back, do you switch on your camera or at least type in the chat that you're back and ready? That'd be great. Right, it looks like we have all of the jurors back. And yes, if you have connection issues, feel free to leave your camera off. It makes life easier. We have team of Singapore, team of Germany, and team of Austria all present as well. Excellent. Right, that seems like we are ready to start the second round of the finals. So in this round, we have Germany presenting problem number 2, oscillating sphere, with Team Singapore opposing and Team Austria reviewing. So since we're all here, we're all ready. We'll start the 5-minute preparation time for Team Germany. And if you want to start earlier, feel free to do so. Just let us know.
Could you please put in the chat the name of the presenter along with the laptop that you would like to have presenter rights?
Can you hear me and understand me clearly?
Yes.
And then I would just have a brief check here. Then I would be ready to start now.
Great, we'll start your 12 minutes.
So hello again, my name is Florian Bauer and I'm now going to report on my solutions to task number 2, oscillating sphere, which states as follows. A light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. This is what this phenomenon looks like. Here we have the same sphere hanging from a wire and rotating about the vertical axis. This here on the left has a magnet placed below it. As you can see, it can freely oscillate. While this here on the left has a magnet placed next to it. And even with the exact same initial conditions, this here on the left stops oscillation much quicker, demonstrating how and when this phenomenon occurs. I will first explain what is to investigate about this task, and then we will separately first look at homogeneous and then inhomogeneous magnetic fields before concluding the findings. So why does this phenomenon occur in the first place? For that, we consider a sphere like this rotating about the vertical axis with a horizontal magnetic field. Because of the movement of the sphere, there's a magnetic force acting on the charged particles, separating the positive from the negative charges, which looks like this. The gradient and the electric field is now because of an electric force, which when combined with magnetic force causes circular eddy currents, which then cause a torque opposing the motion and slowing the sphere down. To get a more intuitive understanding of this, I created an animation showing the charge distribution as well as the current as the sphere oscillates. And you can see it like this. And since both of I can't get the video to work, we just skip that. We'll next look at the case where the magnetic field might be parallel to the rotation axis. In this case, the electric and the magnetic force are equal and opposite to each other, thereby cancel each other out. And with no current, we also have no electric. We have also no torque. What this task in general describes is a torsional pendulum. So we'll take a quick look at that with the stalling torque, the damping torque, and combine this with Newton's second law to solve this ordinary differential equation, which is the same as in all damped harmonic oscillations, so it should be well known. And here we for solution for that looks like that. And we can characterize the motion with 3 aspects. First, the type of motion, a harmonic oscillation, and second, the period, and third, the damping. And since the task asks for how a magnetic field affects the motion, it is all these 3 aspects that could, in theory, be affected. And this is what there is to investigate. Starting with homogeneous magnetic fields, I use this experimental setup, producing the homogeneous magnetic field with a Helmholtz coil and using a fan and thermometer to check for and prevent overheating. I connected the sphere and the wire like this with a non-magnetic screw and some glue. And from below, I placed this lightweight 3D printed part, so that when I took the images with my smartphone and background lighting, everything was black except for 1 circle and 1 line. And then I used a self-written Python script and an a circle detection algorithm to find the center and radius of the sphere. Around that, looked for the brightest spot, so I knew the orientation of the sphere, could calculate the deflection, and then also used Python and Matplotlib for all of the data analysis and visualization. I, of course, also wanted to describe this task theoretically. So here this is what the geometry looks like. We're working with spherical coordinates here, in which the sphere is only defined by its radius and its wall thickness, which should be small compared to the radius. That is our first important assumption, which will later ensure that there will be no radial currents. And another important assumption is that there are only slow rotations. The cited paper here derives the condition for that, and we'll always fulfill this condition. That cited paper also uses this approach to calculate the torque acting on that sphere, where we first consider the generalized Lorentz force, and then with the conservation of electric charge in the steady state, we can combine the divergences of the electric and the magnetic force. So if you use the first Maxwell equation to calculate the charge distribution, you can actually use the magnetic force for that, which you can directly calculate. You can use Poisson's equation to get from the charge distribution to the surface potential, and from that to get the electric field. And then with the electric field and the magnetic force, we can calculate the current, and then take the cross product to find the torque. Cited paper, unfortunately, only derives the formulas here for magnetic fields, which are either perfectly parallel or perpendicular to the rotation axis. And since the task doesn't specify the orientation of magnetic field, to fully fulfill this task, I decided to generalize all of these formulas. However, I followed the same steps as the paper. Starting with magnetic field, which here has any orientation, you of course have to convert everything to spherical coordinates. Next, you find a radial vector pointing to all points on the sphere. From that, get the velocity vector, and then take the cross product to find the magnetic force. Because of the thin shell approximation, you only have to consider the tangential component of this. Now, as earlier stated, you can use this to calculate the tangential charge distribution, tangential charge distribution. And since all of these formulas are, of course, way too complicated to immediately grasp and understand, I brought some visualizations. And this charge distribution has two components. The one on the left is caused by the component of the magnetic field perpendicular to the rotation axis, and the one on the right is caused by the component parallel to the rotation axis. And the next step is to use Poisson's equation to find the tangential potential. However, this step is mathematically quite complex and involves rewriting in terms of spherical harmonics. So we'll just skip that, because in the end, we just find that it is just directly proportional to the charge distribution. With knowing this potential, we can calculate the electric field, combine that with the magnetic force to get the current density. And that looks like this, as we earlier already saw, circular about the y-axis. And now we can take the double cross product to find the torque and take the volumetric integral in spherical coordinates to get this solution for the torque acting on the sphere. And this is one component about the z-axis and one component about the x-axis. However, considering the geometry of the problem, we notice that the sphere can't actually rotate about the x-axis, so this component of the torque has no effect. However, the component about the z-axis will slow the sphere down. And this component is directly proportional to both the moment of inertia and the angular velocity. So we can set up this proportionality factor gamma, which you can directly calculate like this. We can insert this factor gamma as an additional damping factor in the previously shown differential equation. And since you only have lightly damped cases here, we'll still have a harmonic oscillation. The period will remain approximately constant. However, we do get this additional damping term defined gamma, which is dependent on 1, the magnetic flux density, 2, the orientation of the magnetic field, and 3, material properties. We'll have to vary all these 3 parameters and to verify these equations. For the experimental investigation, I also proceeded like this. I first conducted the experiments without the magnetic field, from which I could find out the frictional damping term, and then with the magnetic field, and then I could sum the frictional damping term and the additional damping term caused by the magnetic field to calculate the damping there. Here we can see that in both cases we have very good agreement on both the frequency and the amount of damping. Earlier I said that the period length should not be significantly affected by the magnetic field, so we'll take a brief look at that. Here we can see that for different magnetic field strengths, the period is approximately constant. And even if we zoom in, we see that this is still the case and that the approximation assuming light damping is indeed valid. Much more interesting is, of course, the magnetic damping coefficient. So we'll take a look at that. For different magnetic field strengths, it should be proportional to the flux density. And we can verify this trend and have good agreement between the theoretically predicted and the experimentally gathered data. At this point, I also checked for reproducibility. We're repeating these exact same experiments after a while. And as you can see, we have a very good agreement between initial and repeated measurements, with only deviations in some cases, verifying that the experiments are indeed reproducible. Next, I did what definitely hasn't been done in literature, that is investigate the effect of magnetic fields of any orientation. And for that, experimentally, I just rotated the entirety of the Helmholtz coil to achieve different angles. And here, while we do get some deviations in determining and setting the angle, we can still verify the theoretically predicted trend. Lastly, I varied the material using a zinc, brass, silver, copper, and aluminum sphere. And here the magnetic damping term should be proportional to the ratio of the conductivity to the density. And you can verify this trend. We have some larger deviations, which can be explained by the fact that I used literature values and trying to find out how accurate these are precisely can sometimes be quite difficult. Next, I went on to inhomogeneous magnetic fields, for which I used the same experimental setup, with the one change that the magnetic field was produced not by the Helmholtz coil, but by cylindrical permanent magnets made either of ferrite or neodymium to vary the strength. To describe this theoretically, since the magnetic fields produced by cylindrical magnets can sometimes be approximated as those of created by shorter coils. I found a paper which derives the formulas for that. Here you can see what the magnetic field of a magnet would look like in that case. To verify whether I can use this approximation, I measured the magnetic field strength for different distances and found very good agreement for current equivalence for 10,500 for the stronger and 2,300 for the weaker magnet. Earlier cited paper also derives the torque of an inhomogeneous magnetic field on the sphere with the one condition that the magnetic field has to be axially symmetric. Since this derivation is quite complex and involves rewriting again in terms of Legendre polynomials or spherical harmonics, we will skip that. We can just look at the solution and find out and see that the torque is, to find the torque we have to integrate about the radial component of magnetic field squared. So we can again set up the earlier known differential equation with now this additional term gamma, and while in the underdamped cases we'll still have harmonic oscillation, the period will now be significantly affected, and this additional damping term will now be much bigger. Here we can again look at the period, which is still approximately constant. Zooming in, you can see that we can actually experimentally verify this increase for very strong magnetic fields where the distance between magnet and sphere is very small. Again, more interesting is still the additional damping coefficient. So here we have that for different distances between the magnet and the sphere. And you can see that since the magnetic field gets a lot weaker with even slight increases in the distance, and this is for one an explanation for some of the smaller deviations. And we can still see this in both the theoretical prediction and the experimental data, and verify that even this more complicated model for the theory is still applicable here. Summing up what I've found out and have told you so far, for inhomogeneous magnetic fields, I was able to apply what was done in literature previously to verify these predictions experimentally. For the homogeneous case, I was actually able to go far beyond what was done in previous literature and also verify this experimentally. Thank you very much for listening.
Thank you very much. Right, we move on to clarifying questions from the opponent.
Thank you, reporter. First, what is the thickness of your spheres?
It was very small, usually about 1 millimeter.
Okay, and the radius?
That differed in the mainly used aluminum sphere, it was 5 centimeters.
And how about the small silver sphere?
That had a diameter of 16 millimeters.
I see. Do you vary the thickness of the sphere? I assume yes?
I was not able to do that.
Oh, okay. Do you release your sphere by hand?
Yes, I do.
Okay, what is the max amplitude of the translational swing of your sphere?
I don't have that value prepared right now.
Approximately, will you be able to estimate?
Far below 1 hertz.
No, okay. How many times do you repeat your experiments?
A total of above 50 times, I don't know. For the individual case, I always did 1 measurement.
Okay, thank you. Could you go to slide 7, please?
Sure.
Yes, did you verify the uniformity of your magnetic field?
Yes, I did. You can see these measurements in my appendix slide right here.
Okay, thank you. Did you use constant current or constant voltage?
Constant current.
Okay, could you go to slide 19? How do you calculate the damping time K? Also, not the damping time, but the coefficient.
The C, that's what I got from the experiments without the magnetic field from fitting, and then this is what the C is. The moment of inertia can be calculated, and this additional damping term gamma is seen here on the right.
Thank you. Could you go to slide 20? How do you control the angle of tilt of your coils?
I have them mounted like this. You can see this in the image here, and then I just measure the angle.
I see. Could you go to, how do you ensure the center of your sphere is aligned with the center of the magnet?
By visual confirmation, and in some cases I used lasers to see whether I point at the center of the sphere.
Okay, thank you. I think our time is up.
Yep, thank you. Yep, we will move on to preparation of the opponent. You've got 5 minutes.
Can the opponent please confirm the name of the opponent along with the laptop they would like to have sharing rights?
Right, Team Singapore, are you ready to start?
Yes, please.
Great.
Thank you.
Start the timer.
Good day, everyone. I'm Hilary Chi from Singapore, opposing oscillating sphere. So in summary, the reporter first qualitatively explained the magnetic damping of the oscillating sphere due to the torque on induced eddy currents, and then modeled the damping torque in thin shells using the quasi-static approximation and generalized Lorentz force law. He then investigated field strength, orientation, and homogeneity along with the sphere conductivity. So on to the report. First, I believe the reporter had a very good qualitative explanation of the phenomenon, where he first started with the Lorentz force acting on the moving charges, which leads to charge separation, giving rise to an electric field that finally results in eddy currents that result in the damping torque on the sphere, which enables us to better understand the phenomenon. He also had a clear visualization of the charge distribution, which really helped us understand how the relevant forces in the system affect the sphere. The reporter also demonstrated both experimentally and explained qualitatively the lack of magnetic damping in parallel magnetic fields and accounted for frictional damping, especially since this problem revolves around the effects of damping. He also verified the approximation that the period is constant. The reporter also made use of computational tracking methods to accurately measure the angular displacement of the sphere and verified the uniformity of the magnetic field, which is an important assumption in the first part of his theory. He also maintained constant current to prevent any changes in the field due to heating within the coils. However, I think the report has numerous areas for improvement. Firstly, the reporter has inconclusive experimental trends. We can see a consistent overprediction of the magnetic damping for inhomogeneous fields for both the damping coefficient and the period of oscillation of the sphere. I believe one reason could be due to the fact that the reporter neglected the effect of the finite width of the magnet on its magnetic field in his short air coil model. I think he could model the magnet as a current cylinder of the same width and radius, because this would enable him to account for the effect of the length of the magnet, especially when the sphere is very close to the magnet. As you can see, the deviation is larger when the sphere is closer to the magnet. Next, the reporter has poor experimental control. For example, in his videos, we can see a large swinging, and I think especially for inhomogeneous magnetic fields, because the field strength varies greatly when the sphere is off-center from the magnet. This will result in the average magnetic field experienced by the sphere to be much less, which could lead to the overprediction of the damping in his theory. So I think he could construct a simple clamp release to control the initial angular displacement and position of the sphere accurately. There was also a large error in the angle of tilt of his coils of about 10 degrees, and I think he could attach a plumb line and protractor to the horizontal bar connecting the coils to accurately do this. Next, the reporter had a lack of discussion into the limits of his theoretical assumptions. Firstly, his thin shell assumption, which I think may not be valid for the very small silver sphere. In addition, he did not explain his assumption of the slow rotation of the sphere, and I think this neglects interesting physics in terms of self-induction, where the magnetic fields of the induced currents in the sphere are significant, and in fact would result in the overall magnetic field within the sphere to decrease at high angular velocities. There was also no consideration into thick-walled or solid spheres, which I believe is an important part of this problem, as there will be increased damping due to larger eddy currents, and we would observe radial currents present in non-uniform fields that the reporter chose to neglect. And the reporter could extend his theory with the existing physics by solving for the electric potential within the sphere material. Next, the reporter also neglected the moment of inertia of the cylinder attached to the bottom of the sphere, which would be significant for lighter spheres as it increases the period. And lastly, the reporter neglected ferromagnetic spheres, despite varying the sphere material. And I think this will be interesting, as the magnetization of the sphere will increase the eddy current strength, but at the same time, we could observe self-induction at lower angular velocities. So I would now like to invite the reporter up for a discussion. Could you please share your slides? Thank you. And go to slide 15, please.
Yes, for that I just need the present rights.
Yeah, slide 15.
I can't show it yet. I don't. I need one of the moderators to give me the.
You should have them.
I don't.
Could we pause the clock while waiting? Thank you.
You should have
Yes,
them now.
now I do have them.
Yeah, we'll give you an extra 20 seconds at the end.
Thank you very much.
Yes.
Yeah.
Which slide? 15?
Thank you. Slide 15. Yes, slide 15. Yeah, I just like to clarify. It's the talk about the x-axis. It's the talk about the z-axis that has the damping effect on the sphere, right?
Yes, exactly.
So I think there was some error in the slides, because you said that the talk about the z-axis is the one that has no effect on the sphere's oscillations. Just wanted to clarify this.
And no, it's a talk about the x-axis, since the sphere can't rotate in this direction. That has no effect. About the z-axis, it slows the sphere down.
Right. Okay. Glad that we agree on that. Could you go to slide 27 then? I'd like to talk a bit about the inhomogeneous magnetic fields. Yeah. So will you be able to yes, this slide. Thank you. So will you be able to account for the error bars in your experiment?
Explain them.
Yes. Thank you.
Yes. So for the 6 measurement points on the right, there were many periods observable. So I took the length of 10 periods, approximated the error of that, and then could divide by 10. And for these 2 measurement points on the left, since only 1 to 1.5 periods were clearly observable in the measurement points, we have much larger errors here, because of that.
I see. So you are saying that because you had an insufficient number of oscillations in each run for the closer distances due to the large damping, you weren't able to collect data properly.
Exactly.
I see. Well, actually, but I don't really see how that would cause the error deviation to be so large, because if I release the sphere in the middle of the magnet, I don't think there would be such a significant deviation in the field strength, which would then affect the damping time across runs, right? Because it yeah, go on.
I'm not sure what you mean by this.
Okay.
If you only look at the errors here, this is the actual. This is actually how precise the errors can be measured.
Yeah.
Here, I ran each experiment for 1,000 seconds. That would be just shy of 20 minutes. Took a photo every 2 seconds, and then you can see here I determined the length of. I was able to determine length of the first period only, so that's why you have a.
Okay, but I'm more interested in the consistent over prediction of your theory. Like if you go to the next slide, yes, we can see over here that also similarly for your neodymium magnet, you actually predict a much larger decay coefficient than what you observe. So actually what I was thinking was that there could be 2 possible reasons. And I'd like to first discuss what I think would be a theoretical reason why. So I think that the finite width of the magnet could be important at the closer distances. Could you go back to your previous slide?
I have actually, if you, sorry, didn't mean to show that.
Yes.
If we look here, I actually took many more measurements of the magnetic field around the magnets for the approximation. I do get that the finite length could, in theory, influence this. However, here we see the magnetic flux density in that direction for different distances. For different distances. Here,
I think it's quite commendable that you took more measurements, especially when it's closer and the magnetic field starts to deviate quite a bit. But I think, okay, maybe previously I mentioned about the current cylinder. That might not be the suggestion, the source of the error. But I think maybe another reason could be the swinging. So just now I tried to ask you about what was the amplitude of the translational swing. I think we had some miscommunication. What is the maximum that the swing is displaced, the sphere is displaced by? Parallel to the magnet.
There is ideally, there's of course no translational swing. But for rotational amplitude, that was at the beginning always set to approximately a 1 full rotation, so 6.3 radians.
I see. Well, I don't think it will be. I don't think it's quite possible for you to release it with no swing, right? Especially since you released it by hand. So what I was thinking is that, because when the sphere swings, will you agree with me that it's the axial magnetic field of a magnet that's usually the strongest? The component directly perpendicular to the component along the magnet's axis, that's the strongest.
Yes, mostly, yeah.
So when the sphere translates, right, effectively what that means is that the average field strength experienced by the sphere decreases because when it shifts off from the center, and especially also because in your theory, you assume that the center of the sphere is always aligned with the center of the magnet, right?
Yes, that is an assumption.
Yeah. So I think that because the average field strength experienced by the sphere is lower, that causes you to actually over-predict the damping experienced by the sphere. What do you think of this?
I would mostly disagree. because the translational swing was very minimal. In the video, I know that that there is some translational swing observable. However, this video was made for demonstrational purposes, so I wanted to minimize the period length so that video doesn't get too long. So I used a very short wire. In the actual experiments on the other side, I used a wire as long as possible, at 1.85 meters. So simply because of that, the translational swing is already much more smaller.
Okay,
and,
I understand.
And to state a different possible reason, and there can also the magnets often aren't produced perfectly. The magnetic field, due to production imperfections, can just be off by a few angles. The North Pole isn't very.
Okay, I understand. Thank you very much. I think what you could do would be to verify the radial field also and compare your theory to check. So that concludes this point. I would like to move on to the next point, which is about the assumptions in your model. So could you go to slide 9, please? Thank you. Yes. So over here I noticed that there are some assumptions that you made. So perhaps we could start with the assumption of the thin shell. What do you think? What's the significance of this assumption?
This assumption is quite significant for deriving theoretical formulas, as ensures there are no radial currents. However, even and in my experience, this condition was also always given. But if we have the charge distribution, then the gradient is anyways much bigger in the tangential component than in the radial component. So even if we have if it's not perfectly thin, this still shouldn't have an effect.
Yeah, I see what you mean. But do you not think that perhaps for a solid and thicker sphere, or a sphere that is thicker, what do you think we will observe then? Because I think that there could potentially be radial currents, and because your model only considers the tangential currents, that causes us to not really be able to fully explore this problem.
Yes.
A thicker shell or a solid sphere?
Sorry, could you repeat the question again?
Have you tried a thicker shell or solid sphere, or qualitatively, what would you expect?
Qualitatively, I would expect no significant difference. I wasn't able to do that because I just couldn't get my hands on any of those spheres.
I understand.
I couldn't find out where they are produced, where I can buy them. Also, if you look at a sphere is often considered to be the shell of a ball.
I see. Okay, that's all right.
So I don't think this is really within the task.
Okay, well, actually, I think, right, firstly, for a solid or thicker sphere, what is especially special about this case is in the non-uniform, inhomogeneous fields that you have investigated, which is the fact that actually in an inhomogeneous field, there would be radial currents within the solid or thin shell, in solid or thick shell, because of the radial component of the magnetic field. So I think this would be an interesting part if you could investigate, and how we could modify your theory if the existing physics would be to solve for the potential both in the center and the volume of the sphere.
It would, of course, be quite interesting. However, I stuck to those things which are definitely within the task.
Okay, I understand. Well, thank you. And I would like to move on to our next point, which is another assumption that you made. At the bottom of slide 9, you said that you made the slow rotation assumption. So,
exactly.
Where do you think it's valid, and what happens if we exceed this assumption?
This assumption is important because if it's not the case, then there will be a shock because the current will create a second-order magnetic field in the sphere, which will create a second-order current, which will create another second-order magnetic field opposing the original magnetic field, and thereby reducing the amount of the damping. The cited paper here derives the condition for that. This factor beta has to be much smaller than 1, and in my experiment, it was never larger than 0.001.
Could you explain, right, where you got B from? Sorry to interrupt. Where do you get B from? Like, how do you calculate B? Is it by making use of the magnetic vector potential?
No, it is by this formula, the magnetic permeability.
Okay, I see. Well, I think you could try to investigate this self-induction by using a solid sphere and also a wire with a higher torsional constant. So, for example, a shorter wire, because that will give you a higher torsional constant and it will take faster.
Because beta is so small here, so there's almost no magnetic field.
Okay.
It's just not applicable here.
I understand. It's quite hard to achieve it experimentally.
Right, I'm gonna have to interrupt you there.
Thank you.
And yep, And we'll do a summary from the opponent.
Okay, thank you, reporter, for the discussion. So firstly, we clarified his qualitative explanation in his slides. That's actually the torque about the z-axis that results in the damping rather than the x-axis, which the z-axis is the rotational axis of the sphere. Next, we discussed the large deviations in his theory and experiment for inhomogeneous fields, and we agreed that the air coil might be a good enough approximation, but I do think that the reporter could have taken more data in order to ensure that his model agrees, including verifying the radial fields. And another source of error could be the release error due to swinging, which results in a lower average magnetic field. Next, we talked about the thin shell assumption that the reporter made, and I disagree that the thickness is unimportant because, especially for the parameters investigated by the reporter, such as a non-uniform field, there will be interesting radial fields present. And lastly, we discussed self-induction. And I think that while I do agree that the reporter is unable to achieve this experimentally, he could have made modifications such as a solid sphere to investigate this. So in summary, due to the limiting assumptions made by the reporter and that he only considered thin shells, I think that thicker and solid spheres will bring greater physical insight, and he had large experimental errors. So I think he has not sufficiently explored the problem statement. Thank you.
Thank you. Right, we will move on to questions from the reviewer. Do we have Team of Austria ready for questions from the reviewer? Maybe some technical problems. Oh, all right. Okay. Well, try to swap computer quickly or go to somebody else who's using another computer.
Can you hear me?
Yes.
Wait, there's like this positive. Ich höre jetzt nichts. Wait.
Yeah, there's some feedback.
Okay. Does it work now? Can you hear me?
Yes. Yes,
Okay,
that's
great.
fine.
Sorry for
Feedback.
this quick interruption. So I can begin with the questions now. Okay, so my first question to the reporter will be, did you ever try to verify the charge or potential distribution experimentally?
No, I haven't done that, and I wouldn't know how that's possible.
Okay. The second question to the reporter, so you assumed a steady state in your theory with a constant omega, but we know that the pendulum has a constant change in like velocities, which induce further charge, not part of your theory. In which regime does your consideration of the steady state break down?
Definitely not in the regime I am in because it's just it's just a very small time dependency. It's approximately a steady state.
Okay. Do you think this would be like an interesting thing to further investigate? Maybe when your theory breaks down?
Theoretically, yes, that would be quite interesting. However, I don't think this is experimentally achievable in any way.
Okay. So, short answer to the opponent. How would you think the thickness of the sphere would affect the torque?
The magnetic damping torque on the sphere would increase.
Okay. To the reporter, do you agree with this opinion of the opponent?
Yes, but the change would be very minimal.
Okay. So another question to the reporter, is the power dissipation of the eddy currents a relevant dampening effect?
No, it's not.
Okay. Would the opponent agree with this statement by the reporter?
I believe the power dissipation is accounted for in the loss of energy of the sphere.
Okay. Next, to the opposition, how does the magnetic permeability affect the dampening, as you mentioned in your opposition speech?
If the magnetic permeability of the sphere is higher, the damping will be greater.
Okay,
because the magnetic field within the sphere will be
yeah,
higher.
that's fine. Thank you. To the reporter, you stated the error source for the systematic underestimation in your homogeneous field experiment is due to error in the magnet production. But then you both modeled the magnet and experimentally verified the magnetic field. Where are these errors in the production then? I don't think I quite understood that.
Having worked with similar magnets before, I was able to find errors like that with similar magnets. And here you can see that the maximum of one of the field components isn't where it theoretically should be. This could be a measurement inaccuracy. It could be a production error. It's just a possible, but I think very likely source of that error.
Okay, and you think this is the only error source, and there are like no other error sources in this?
No, I haven't stated that. It's just I didn't say that's just the main source.
Okay.
Probably.
Okay. Thank you. I think we're out of time. Thank you.
Thank you.
Yes. Thank you. We'll go on to preparation time for the reviewer. You've got 4 minutes.
Kann man irgendwie die Kamera ändern? Okay, so I think I would be ready to start.
Yes, go ahead.
Okay, dear ladies and gentlemen, my name is Jeremias Costa, and today I will review the fight of the problem number 2 oscillating sphere. I will skip over the problem statements since I don't think it's relevant. Now, for a quick overview of the report and some feedback, there were many positive aspects. He had a decent qualitative explanation and determined the charge separation and the resulting eddy currents as the main source for energy losses and the dampening torque. He had an extensive theoretical model for the homogeneous B field, where he modeled the charge distribution caused by the magnetic fields perpendicular and parallel to the rotation axis, and then he derived his own application of a theory he got from a paper, and he then used a damped harmonic oscillator model, which we found to be appropriate. He then had a theoretical model of an inhomogeneous B field, where he modeled the B field itself with an experimental verification, and he used a paper for the torque modeling. For possible improvements of the theory, we believe the science communication for the theoretical model of the inhomogeneous B field quite unclear, and we did not see where his own contributions really came in. Also, there were unclear limits of the theory. We believe with high changes in velocity, the damped oscillations should become inharmonic, since there will be high energy losses when the direction of the currents change. So, and there was it was unclear if the power dissipation of eddy currents affect the dampening. For the experiments, he had a great parameter variation. Great parameter investigation and effect on the period length and the decay coefficient with 3 different parameters varied. He had an experimental setup for the inhomogeneous B field, which we found impressive. And also there was a great overall agreement between both theories and experiments. For the improvement, we think the experimental determination of the potential gradient could have been investigated. For example, you could have used a voltage measurement device on the sphere using using a measurement device that drags upon the surface of the sphere. There were unclear error estimations and no mention of error sources. The investigation into the sphere thickness would have been interesting, and there was shaking visible in the videos. Now for the feedback for the opponent, he asked some relevant questions, including sphere thickness, release of sphere and repetition, and the alignment of the angle and variation. He had very efficient time management during the clarifying questions. He mentioned the overprediction for the inhomogeneous field. He pointed out the lackluster discussion of error sources and unclear error bars. We agree with them on that point. He mentioned that the magnetic permeability of the sphere changes the field within the sphere, which we think was quite interesting. And there was also the mention of the lack of reproducible clamp release, and he mentioned possible limits of the typal approximation of the limits. However, there was also poor prioritization in the speech and irrelevant points like the moment of the inertia and the tracking ring. They did not mention the lack of consideration of the power dissipation by eddy currents, or even like if this was relevant, and they did not manage how current density distribution on the sphere changes with angular velocity. Now for a discussion summary, first discussion topic was additional induced magnetic field. The reporter stated that he showed additional calculations for the induced magnetic field, and the opponent did not state a clear opinion. We thought it was impressive that this effect was considered. Then they talked about the error bars. The reporter said that only few oscillations in some cases were in effect, and the opponent doubts the effect on the error size. We agree with the reporter's explanation. They talked about the overprediction of the decay coefficient. We thought the dipole approximation of the opponent seems valid. Also, they talked about this again, and we agree in this case with the reporter, since the swinging was probably not the main error source. Thank you for your attention.
Thank you. All right, we will go on to concluding remarks of the reporter, assuming that they have had their screen sharing rights back.
Yes, so I have a few different aspects to talk about. I won't talk about the release mechanism because I believe I have adequately justified this during the discussion, and because the suggestion by the opponent is, in my opinion, quite unrealistic. However, I will quickly talk about thicker shells again. I don't think that this is what is directly specified by the task, and additionally, neither opponent nor the reviewer are able to state a reason for why this should have a strong, significant effect, assuming we aren't talking about wholly solid spheres here. One of the limits of the theory, which mentioned by the reviewer, was when the damping is so big that there's no oscillation anymore. We can have investigated this too, but didn't include this in the report because, again, this is the oscillating sphere. Here you can see what that looks like, just an exponential decay. And then lastly, regarding the errors, the main error source is in determining the deflection because the line has a finite width. And then I used error propagation from fitted values with the SciPy library for Python.
Thank you. All right. Thank you for those 3 stages of this round. We'll move on to questions from the jury. And yeah, please raise your hand. I'll start with a question for the viewer. So you talked about the power dissipation by eddy currents. How large is this effect compared to the other effects presented by the reporter?
So so in our opinion, it's like not necessarily even a large effect. We still believe this could have been like interesting to investigate and like even mention that there are these like power losses. It's not it doesn't have to be like a huge effect, but we still think it would have been interesting to like, this is just a minor criticism, and we just think that this could have like been like the cherry on the cake, maybe, you know, if you understand me.
Okay. Yeah, no, I get it. Thank you. Ioannis?
Yes, I have a quick question for the reporter. So the spheres you used were hollow, correct?
Yes, exactly.
What would the difference be in your experimentation, or would we even observe the phenomenon had the spheres be not hollow, be completely dense?
I think there would still be the dampening. I don't agree with the opponent that this effect would be larger. Actually, the paper which I cited here, there's a follow-up paper to that for thicker shells, and according to that paper, at least not for a finite width, according to that paper, it's the same amount of dampening with thicker shells.
Okay,
it's just I haven't included that because I don't think it's too relevant for this task.
Okay, thank you very much.
Okay, Maria?
I have a question for the reviewer. In your opponent. In your opposition speech, you mentioned that he used the thin shell assumption, and that you don't believe that this might be applicable to the sphere he used. So I would like to ask you why do you think that is?
Yeah. Oh, okay. So I think that is particularly not applicable for the silver sphere because the reporter mentioned that the thickness of the wall is 1 mm while the radius of the sphere is 8. And I think that this ratio of about 12.5% is way too large for us to consider that there are no radial currents within the sphere.
Since this is incorrect and was a misunderstanding, I would just say that the thickness for the silver sphere was much lower than 1 millimeter. I said that most spheres had this, and specifically the silver sphere was thinner because it is so small.
Okay, Carrie?
Hi, I just want to check, and it kept coming up from different people. Maybe I think my notes indicate that it was probably the reporter who was saying that the power of the eddy currents was relatively small. So the system is losing energy. It loses energy faster than it would. So where does the energy go?
The energy eventually it's thermal energy in the sphere.
So how does it become thermal energy?
In the process of getting slowed down, where according to Lenz's law, it has to always oppose its cause. I think in this process the sphere will slightly heat up, but only very minimally.
Okay, thank you.
Okay. Luis?
To the reporter, you made a lot of measurements. Do you think the wire hysteresis is important?
No, I don't think it's important because compared to the sphere, the wire is just so very thin that just doesn't have an effect.
Okay.
Also, it was a copper one, so that's not it's not ferromagnetic.
Okay, Clem?
The question for the opponent: what is the maximum relative change in the decay could be produced by changing the thickness of the sphere? So what is the effect of thickness? It is 10% or 2% relative in the decay?
Are you trying to say comparing a thick shell theory or just the thin shell when we change the thickness?
Yeah. If you change the thickness, for example,
Okay, so
the magnitude.
Okay, I'd like to clarify this point of the discussion. So the damping torque on the sphere is proportional to the thickness. However, the reason why the reporter explains that there is no change to the damping time of the sphere is because the moment of inertia of the sphere is proportional to r to the power of 5. Proportional to r to the power of 4 multiplied by the thickness, and it's the same for the damping coefficient. So on the overall, this means that the damping time is the same.
Thank you.
Right. We're going to have to stop there. Sorry to all the jurors, Alice. I know that I think we could spend probably 20 minutes asking questions to these poor competitors. So, right, we will go on to grading. And with grading, put it into the grading system, and then we'll repeat the process from the previous round. All right, we have scores in from all of the jurors. So same as last stage, I'm going to ask the highs and lows for the reporter, opponent, and reviewer to justify their marks without sharing what the mark is. So we'll start with the reporter. So on the low end of the scale for the reporter is young one.
Okay, I think for the reporter, in the presentation, there's too much derivation about the equations. And in their theory, only the rotation were concerned, and also in the experiment. So apparently they try to avoid any swinging of the sphere, and which should not be excluded in the investigation. So that's why I cannot give a high score for them. That's all.
Okay. And high for the reporter, we have Klim.
Yeah. So what I liked on that report is that literature review was done, and also after that it was a novelty improvement in case of the article work. And so after usual qualitative explanation, theory made out of articles, so it was an improvement that I liked, and it was mentioned in the report, highlighted that that was done by us and that was not our work, and that's how science is done. We go further because we stand on the shoulders of giants.
Thank you. I just like to point out I like the report. I wrote down here, this is the danger of demonstration videos. You make a video like, oh, I'll make it sort of a nice demonstration of the phenomenon, and you do something slightly different to what all of your experiments are, and then everybody focuses on, oh, but look, it's swinging rather than rotating. Oh, that's not what I want to do to look at. Anyway, that's the danger of demo videos. Right, so for the opponent, we have a low for the opponent from Carrie.
I just felt that there was just a whole lot of stuff about errors that was going on and on about errors without looking at the phenomenon and the modeling and the assumptions behind the modeling. It was just about this graph, these lines don't quite meet these lines, and these error bars are big, these error lines are small, and just thought, we aren't really getting to the issues here. So yeah, so that was it wasn't a fantastic score because of that. It was okay, but just don't really want to listen to a discussion about errors unless it's critical. But I think it was much more that could be done.
Okay.
And I did think that in some places she was being a bit harsh, just a bit, a bit aggressive.
Well, to counter that, we have a high for the opponent from Klim. Oh, you're still muted.
Is it okay now?
Yes.
Oh, you see, all grades I explain are high grades, so probably it's just because my relative grade is higher than from other jurors. Yeah, but what I liked is that speaking about not the work, is that opponent spoke about the work done by the reporter, about assumptions he made, and she improved the work. She improved the report made by reporter. So that was opponent is needed here to help us understand what have been done and to improve the work.
Thank you. And we'll do the reviewer last. And let's repeat a favorite. Carrie, would you like to comment on your low for the reviewer?
Oops.
As long as we're
well, start
consistent
within the
through all
questions.
parts, that's fine.
The questions. I think a question from the reviewer which starts, "Do you think it would be interesting?" was not really a great question.
Hard to understand. So that's why I add some points about that. Okay, that's all.
Okay. Well, thank you. Thank you very much for this round. Another round of excellent physics. And we'll take a break, and we will be back then for the final round of the finals. So if everybody could be back here at the 1/4 your local time zone, and we can start the last round then, that would be fantastic. Thank you all very much.
Hallo? Hallo? Jetzt geht's.
All right. If all the jurors could either turn their cameras on or put a message in the chat to say you're back. If I could have the teams come back on the screen, that would be great. So it looks like we got all the teams. We're missing 2 of the jurors still. Missing 1 of the jurors still. Right. Young one, are you here? You back? Right, okay. All the jurors are here. So welcome to the final round of the finals. So in this round, we have the team of Singapore presenting problem number 7, Faraday waves, with team of Austria opposing and team of Germany reviewing. And since we're all here, I think we'll start the clock for 5 minutes of preparation time for team of Singapore. If you would like to start earlier, just let us know.
We would just, so the team of Austria would just like to point out like that we have this whiteboard at the camera of I think Jeremias Costa's the account. So during the discussion we might use this. I don't know if you can see the line on there.
Yeah. More than happy to have you use the whiteboard. So I think the person has presenter rights at the time has to like invite other people to be allowed to draw on the whiteboard.
Oh, in our case, it's like
it works simultaneously.
Yeah, it's like a camera. You can just go through the active cameras, and then you can see Jeremias Costa, and then you should like see a smiley.
Cool. Good.
Okay. Just wanted to point out. Thank you.
Could the name of the presenter, opponent, and reviewer please be put in the chat along with the name of the laptop that they want presenter rights for?
Is it possible for us to start a bit earlier?
Yes, absolutely. Please go ahead whenever you're ready.
Okay. Hello everyone, I'm Luke Mazaru and I will present on problem number 7, Faraday waves. The problem statement tells us that a less viscous droplet floating in a more viscous bath may develop wave-like patterns when the system is vertically oscillated. We are to investigate the parameters relevant to the production of stable patterns as shown. Here's my content for today. Firstly, some preliminaries. This is my experimental setup, which uses a speaker to induce vertical oscillations. A Petri dish is used to contain the liquids, and an accelerometer measures the magnitude of oscillations. Lastly, a camera films the Petri dish from above. Firstly, I will explain what Faraday waves are. When a fluid bath is oscillated at a sufficient amplitude, we see that waves form on the surface of the fluid. These waves are Faraday waves and require a minimum amplitude to form. Now, we consider a floating droplet. Above threshold, Faraday waves form on its surface. These waves cause the shape to change, in this case into a pentagon, thus changing the wave pattern on the droplet. Hence, these two effects drive each other until an equilibrium is reached. If the amplitude of oscillations is increased, another equilibrium shape is obtained. If we then decrease the amplitude to its original value, if we then decrease the amplitude back to its original value, the drop is no longer a pentagon, but it appears elongated. As such, the final shape of the droplet depends on its initial shape, suggesting hysteresis. In total, we can observe 3 different equilibrium drop shapes under these conditions. To determine the droplet shape, we binarize the video and use edge detection to determine the droplet profile. Looking at the system from an angle, the Faraday waves on the pentagon have 5-fold symmetry, and those on the elongated drop are parallel lines. Finally, from the side, we see that the bottom interface has no Faraday waves and is horizontal within a region. Now, I will qualitatively explain this phenomenon. Firstly, we consider a region around the contact line. Animating the Faraday waves, we see that they are standing and must consist of waves traveling in opposite directions. These waves reflect at the edge of the droplet, causing an outwards wave radiation pressure. We note that the Faraday waves have a uniform wave number on the bulk of the droplet, except at the edge where the height changes rapidly. Furthermore, the waves have a peak or trough right before the edge. Therefore, the possible wave numbers are controlled solely by the droplet shape. However, Faraday waves also follow their own dispersion relation, closely related to that of surface waves. The ideal or most stable wave number is then decided by the driving frequency. Now, we can explain the droplet evolution. The wave number from the dispersion relation does not match the initial droplet length, and it would be more stable if it matched this wave number. So, the droplet elongates such that the wave number shifts to its ideal value. More complex shapes can also be formed as long as the surface tension and wave radiation pressure equalize when the droplet stabilizes. Now, I will move on to my theoretical model. Firstly, I will cover the fundamental assumptions of our theory. From the side view, we can draw the mean profile of the droplet. To the left of this line, the drop is flat, which we denote the infinite bath region. The rest of the droplet curves down to the contact line and is denoted the meniscus region. Theoretically, we will solve these regions separately. There are also 3 relevant timescales to this problem: the wave oscillations, the Faraday waves, and the droplet evolution. The wave oscillations occur at the fastest timescale of the forcing frequency, followed by their evolution, and finally the droplet evolution. We will explain these expressions later and solve for each regime independently. We can split our theoretical model into 3 sections: solving for the wave profile on the droplet, solving the amplitude of the Faraday waves, and evolving the droplet according to the wave radiation pressure. This process is cyclic, and we will first solve for the wave profile. From prior work, we know that the wave profile on the droplet obeys the Helmholtz equation with the wave number as its eigenvalue and has a contact angle of 90 degrees with the edge of the droplet. We can decompose this solution into a sum of plane waves, which will then determine the wave amplitude. Next, we solve for the Faraday wave amplitude. We solve the fluid dynamics in the vibrating frame and modify gravitational acceleration with A as the forcing amplitude, modeling a layer of fluid with height h. With Faraday waves, we denote the displacement of the surface as zeta and use Navier-Stokes and continuity to get this expression for the fluid velocity. For the boundary conditions, we define a horizontal gradient, impose no slip at the base of the droplet, and the kinematic boundary condition at its surface. Defining tangential and normal unit vectors, we impose no shear stress and balance the normal stress with the surface tension. We now perform a multiple scale expansion on the equations, defining epsilon as the ratio between wave oscillation and growth timescales. Solving to third order, we get this general solution for the vertical velocity in the bath and the wave height, with C representing the wave amplitude. We get this amplitude equation, including the growth rate and an interaction term. F depends on the angle between plane waves, with higher values of F meaning more dissipation. Now, we can plot whether Faraday waves form at all possible wave numbers and forcing amplitudes. Above the line, the growth rate is positive, so Faraday waves are formed. Zooming in, there is a critical acceleration and wave number required for their formation. Plotting this wave number against the frequency of oscillations, we observe an increasing trend. As such, the wavelength decreases with increasing frequency. We can also plot the critical acceleration against angular frequency and also see an increasing trend. This occurs as higher frequencies have shorter wavelengths, increasing the curvature of the waves and the damping from surface tension, thus requiring a greater acceleration amplitude to overcome. Now, we can investigate values of accelerations above threshold. Plotting the growth rate against the wave number, we see that there exists a maximum growth rate, which determines the ideal wave number, and that the droplet will evolve to maximize this growth rate. For one wave vector, this is how the wave amplitude depends on the forcing amplitude. Below A crit, no Faraday waves form, but above A crit, the wave amplitude increases with the forcing amplitude. Lastly, we solve for the evolution of the droplet. From the side, we can balance the pressures at the edge of the drop, accounting for surface tension, viscous damping from the bath, the hydrostatic pressure, and the wave radiation pressure. To obtain the wave radiation pressure, we get the momentum flux density at the edge of the droplet. We then time average the equations and note that the functions are sinusoidal, thus cancelling out the linear terms to obtain the wave radiation pressure. We also apply the lubrication approximation to our system. Now, we move on to a top view, describe the boundary in polar coordinates, and write the evolution equation at the edge, which I have derived myself. We then assume that the Faraday waves reach steady state much faster than the droplet evolves in order to find the wave radiation pressure acting on the edge. In summary of our theory, we must first solve for the wave profile given the droplet shape, and then use this to solve for its amplitude. And then finally, we can evolve the droplet, iteratively solving until the droplet shape stabilizes. Now, we will show our experiments. Firstly, we will classify the different droplet shapes formed. At one frequency, we observe different shapes at different accelerations and name them as such. To understand when these regimes occur, we experimentally obtain a phase plot of the different regimes. We see that at low accelerations, the droplet remains a circle as the Faraday wave amplitude is too low to deform it. Above a threshold, the droplet evolves into deformed and elongated droplets, and if the acceleration is further increased, worms begin to form, which are unstable. We will explain the hysteretic region later. Firstly, the elongated regime. For this regime, the droplet has only one wave vector and is longer on its axis. We denote this length as L and the width of the droplet as W. We can plot L against the acceleration amplitude to obtain this graph. Increasing the forcing amplitude increases the wave amplitude, causing the droplet to elongate. Increasing the frequency decreases the wave amplitude, so the droplet length decreases. We can also plot the droplet shape and see a good agreement between our theory and experiment. Next, I will cover the deformed regime. Here, more complex shapes are formed and different shapes are formed at different frequencies. Focusing on one of these shapes, we get this graph defining its outline in polar coordinates. Taking the Fourier transform, we see a peak at mode 2 and smaller peaks at higher modes. This Fourier transform is unique to each shape and helps us to classify it. As such, we can plot the strength of dominant modes at different frequencies and observe regions in which different modes are dominant due to the different shapes formed. This happens since the frequency determines the ideal wave number, which then determines the shapes formed. Now, we can focus on the pentagon and see that it only exists in a small range of frequencies. Expanding this range, we observe two axisymmetric modes and classify them as such. We can use our theoretical model to predict the stable frequencies for both modes at different droplet volumes. Larger drops require a greater wavelength forcibility, thus decreasing their stable frequencies. We can also increase the droplet density by decreasing the alcohol concentration, thus increasing its height. With the same volume, a thicker droplet has less surface area and is smaller, so a shorter wavelength is needed for stability, thus increasing the stable frequency. Lastly, we can also theoretically predict the droplet shape, which is experimentally verified. Finally, I will cover the transient regime. We can theoretically simulate the droplet evolution, and here we note that it is quite realistic. I will now cover some interesting transient behavior observed experimentally. Starting from a circle, the droplet evolves to a pentagon at amplitude A1. When we increase the amplitude to A2, the droplet becomes a diamond-like shape. However, when we decrease the amplitude back to A1, we observe that it becomes elongated and not a pentagon, thus demonstrating that different shapes occur under the same forcing parameters and showing hysteresis in our system. Now, we will look at steady rotation and oscillations. Here, the droplet rotates at a constant angular velocity. Zooming in, the wave fronts follow a curved path, causing an asymmetry in the wave radiation pressure at the edge. This generates a torque from the bath rotating the droplet, which is also balanced out by drag from the bath. At the edge of stability for a pentagon, we observe that the droplet oscillates periodically with time. This is due to Faraday waves pushing on both sides of the droplet and growing perturbations in those areas, thus causing the points and edges of the pentagon to stop at regular intervals. Taking the Fourier transform of a point on the edge, we observe that the droplet oscillates at one frequency. Finally, I will summarize what I have covered in the report. I have shown the formation of stable patterns and covered computational tracking techniques, and explained the effects of relevant forces and the three timescales on the final droplet shape. Theoretically, I solved the wave profile with the Helmholtz and Navier-Stokes equations and balanced pressure at the drop edge, which was experimentally verified in the deformed, elongated, and transient regimes. I have now come to the end of my presentation. Here are my references, and thank you for your attention.
Thank you. Right, we will have questions from the opponent.
Yes, did you measure the amplitude of the wave oscillation experimentally, yes or no?
No, we were not able to.
Okay, so regarding the eigenmodes and oscillation patterns, what were the highest overtones of the standing waves that you could observe experimentally?
We were only able to observe waves that were oscillating at half of the amplitude of the forcing. Yeah.
Okay, but how many velocity or oscillation nodes could you observe in the Faraday waves until it did not work anymore?
Okay. So I think this is what you mean by the different modes of oscillation. So as you can see here, we can observe many different Faraday wave patterns on the different droplet shapes formed at different frequencies.
Okay, thank you. I think we'll come back to that. You mentioned the lubrication approximation. What assumptions does this underlie?
So the lubrication approximation assumes that the height of your droplet is a lot less than the radius of your droplet. And we have verified it here. It is EH. Yeah.
Why do you think this approximation is justified that the height is a lot less than the radius of the droplet, if it is a flat droplet?
Because we have verified this experimentally over here. As you can see, the height of the cap is much less than the radius of the droplet.
Okay, another question. Did you investigate how the reflection and transmission ratios of the waves on the boundary are influenced by different liquid and oscillation parameters?
We were not able to vary the liquids in the bath, but we observed that there were very little to no Faraday waves in the bath, so therefore the wave should be fully reflected at the edge of the bath. Yeah,
I see.
at
So
the edge of the droplet.
Okay, and then just to clarify, which droplet and which bath did you use?
Okay, so for the droplet, we have used a mixture of isopropanol and water, and for the bath, we have used silicone oil.
Thank you.
Thank you. We'll move on to preparation of the opponent, 5 minutes.
Hello everyone, I'm Elias Koshir from Team Austria, and I'm now going to oppose problem number 7, Faraday waves. I think the problem statement was already covered, so we'll skip that in the interest of time. To summarize the presentation of the reporter, he had a qualitative explanation using a standing wave that is reflected at the boundary, entirely refracted, we should note. He investigated the shape shift of the droplet, and he investigated many different stable shapes, such as pentagons, diamonds, and elongated droplets. He also observed that there are processes happening on 3 different timescales: the wave oscillation in itself, which is very fast, the wave growth, which is also very fast, and the initial regime, and the droplet evolution, which is quite slow compared to these other processes. And in his theoretical model, he also used the Helmholtz equation to calculate the wave profile, the Navier-Stokes equation to calculate the wave amplitude, and he also predicted theoretical thresholds for critical wave number and accelerations for these Faraday waves to occur. And he solved for the droplet's shape using the pressure balance at the edge of the droplet and predicted theoretically the shape of the droplet. So for his experimental setup, he used a speaker setup to make vertical oscillations of the beaker. He investigated the following parameters: the frequency of oscillation, the amplitude of oscillation, the droplet volume, and the fluid properties, where he only changed the density. And he had a nice phase diagram for the different shapes occurring at different oscillation accelerations. And he conducted experiments with the deformed shapes. And he proved that dominant modes lead to different shape forms. And he also investigated rotational motion of the droplet. To go to the feedback, he investigated the change of the wave shapes dependent on the amplitude, and he achieved many wave shapes, which we found very impressive, since he almost achieved all possible wave shapes. He had this assumption to separate it into timescales, which we found valid. He investigated the critical conditions for the Faraday waves to occur, which is very important for the understanding of the phenomenon. And he also investigated extensively the momentum transfer at the boundary and the boundary conditions, where the waves, he said, would be reflected. He observed also a lot of wave shapes and had a nice phase diagram, which helps to improve qualitative understanding. And he theoretically investigated droplet shape and frequency of modes. Now, to the points to improve on, I think the qualitative mechanism of wave formation fell too short in the presentation. He did not mention what actually causes the waves to form and not the droplet to oscillate uniformly. His parameter variation was pretty poor, since he only used one alcohol and one paint and did not vary viscosity or surface tension, which are very important parameters. And therefore, he also did not predict the types of oscillations behavior for different parameters like surface tension and viscosity, which I think would have been very important and was lacking in the report. Also, he did not mention how eigenmodes and resonant frequencies depend on droplet frequencies, like droplet shape, surface tension, viscosity, etc. And he did not experimentally measure amplitude or energy in the system, so he did not consider the damping of the waves due to friction and the driving frequency, and that the driving frequency should, or the resonant frequency should decrease due to dissipation. So to summarize, the qualitative explanation was there, but not complete. The quantitative theory was very extensive. The experiments were really nice, and the comparison was there. However, we would have liked a lot more parameter variation. So I would like the opponent to the discussion, and I would like to discuss these following discussion topics.
Could I have presenter rights, please? Thanks.
Okay. And since I think this was not covered enough in the presentation, I would like to talk about the qualitative mechanism of the waves forming. What is your reason why the droplet forms a standing wave and does not oscillate up and down as a uniform mass.
Okay, I believe that's quite interesting that you brought this up. So here we will show the relevant forces in the system. In this case, the gravity is red and surface tension is in black. So at the initial phase where the waves are going down, you can see that gravity will start to point downwards, and there will be little to no surface tension since the surface of the wave is quite flat. And then this will actually cause the velocity of the water to move towards the side. And then there will still be a damping force from viscosity, but it's smaller than the gravitational acceleration. So now when the waves go back up, there is an additional driving force due to the momentum of the fluid that is going up on the sides. And this will be damped out by surface tension and gravity, but the momentum of the droplet will be more.
Okay, I think I kind of agree with you here, but I think what initially causes that some parts of the wave move in opposite directions when the oscillation starts is because there are slight imperfections and deformations, and therefore the symmetry of the droplet is broken, and we get these standing waves to form. Would you agree with me on that point?
Yeah, so I do agree that you would need some initial perturbation to the surface in order to even get Friday waves.
Okay, thank you. Another topic I would like to discuss are the energies in the system and energy losses that you get. In my opinion, viscosity, for example, or friction should be a source of energy losses. Like if you increase the viscosity, then so to say the springs within the wave should become more stiff. Did you have an investigation, like theoretically or experimentally, on the energy dissipated by friction?
Okay, no, I do not have any plots with me right now of how the viscosity will affect the energy dissipation. But I do believe that if you increase the viscosity, you would expect that your wave amplitude might decrease because more energy is dissipated in the system, and then you would result in a lower wave amplitude. However, viscosity was accounted for in our theoretical model. Yeah.
Yes, I agree, and I also think that just like with an oscillator, we have like a two-dimensional oscillating phenomenon. So if it is a damped oscillation, then the resonant frequency should be slightly below what is predicted by the theory, because we get some losses by friction. Another interesting part of your report, which I quite liked, was your experimental investigation and your phase diagram. So could you maybe please bring up your phase diagram? Yes. Like I really like that you observed these different shapes like worms or pentagons or triangles, like these oscillation modes. What I would be interested is, did you observe sometimes that the droplet breaks and splits up into several smaller droplets or smaller worms, maybe?
Yep. Okay. So in the case where we use a very, very high forcing amplitude, we do observe worm-like behavior over here. And what will actually happen is that these worms would not break up into smaller droplets on their own. But if we decrease the forcing amplitude, for example, we just stop the forcing, you would get that surface tension would kind of pull these two edges into each other. And then you would observe that there will be a break off over here into smaller droplets. But we have not experimentally investigated this.
Oh, okay. I think it's nice that you have this slide, and I agree that when the acceleration, so to speak, of the speaker or of the wave becomes too high, then the surface tension cannot sort of resist the oscillation motion, and therefore the droplet breaks up. Okay. What I also would like to discuss are the edge effects. Could you maybe go to the slide where you concluded that the waves are reflected on the boundary between the droplet and the bath? Yes. Please explain to me why you think the assumption that the wave is entirely reflected is justified, and that there is no momentum transferred to the other fluid, and the wave also propagates to the bath.
Okay. So for this, I believe that we should look at the ratios of the viscosities between the bath and the drop. And as you can see, the ratio of the viscosity is on the order of about 1,000. So since the bath is so much more viscous than the drop, effectively the bath behaves as a solid wall, and you get that there is a pure reflection when the wave reflects at the edge of the droplet of the bath.
Okay, I think I kind of disagree. Like, if you see what I'm drawing, I think that yes, most of the wave is reflected at the boundary. However, every time you have a boundary, no matter if it's electromagnetic waves, rope waves, or water waves, there's always something transmitted and always something reflected. And so I think therefore you should also observe that there's a wave spreading out on the outside, at least for at least slightly, or for certain parameters of the droplet.
Okay, yeah, I do agree that, for example, if you use a greater viscosity of the droplet, then we might observe waves reflecting off. But for the parameters that we have used in our experiment, the transmission of the waves into the bath is really damped out due to the extremely high viscosity. So as you can see here in this like very zoomed in photo, there are basically no oscillations in the bath.
Okay, so you're saying that the bath is the viscosity of the bath is orders of magnitude greater than the droplet, so this is negligible, at least in your experimental setup.
Yes.
Okay, I kind of agree. However, I think a point where you could have improved your experimental investigation was to investigate a lot more parameters, like the viscosity of the droplet and the bath, because I think that the difference in viscosity has a very big effect. So I would expect that if you use a droplet with higher viscosity, the oscillation becomes more stiff, and therefore you get so to speak, a smaller oscillation frequency, for example. And I think it would have been really nice to see how these parameters affect the oscillation modes and eigenfrequencies of the droplets.
Okay, so what I believe you're asking is for us to investigate different viscosity ratios of the droplet and the bath. Is that right?
Yes. So maybe my question is, so if we would increase the viscosity of the droplet, how exactly would you expect the oscillation behavior to change?
Okay, if we increase the viscosity of the droplet, I would expect that the oscillation amplitude of the Faraday waves would decrease. So in this case, you will need a greater acceleration before Faraday waves are even formed in your droplet. So for example, this graph, you will observe that the line would shift up. But other than that, I believe that most of the qualitative behavior of the droplet will still be very, very similar, and you will just get that you will need a greater acceleration.
I agree with you that the critical acceleration would move up if the liquid is more viscous, because it might be more inert. But I also think that it would have a difference on the frequencies that you would expect, because the particles within the droplet, if it is more viscous, move up and down more slower and resist the motion. Therefore, you should get a larger frequency.
I agree with that. Yeah.
Okay, and one thing I would also discuss is the surface tension. So, in your opinion, how does the surface tension affect the oscillation frequency?
Okay. In my opinion, increasing the surface tension would increase the oscillation frequency of a certain wave number of the Faraday waves, because now there is a greater force that is kind of restoring the Faraday waves back to equilibrium, and therefore you will observe that the Faraday waves will start to oscillate faster given the same curvature, which is decided by the wave number. Yeah.
Yes, I agree with you. And one final question. Would you think that that the waveform of the oscillation, like a triangular wave or a square wave, would affect the oscillation?
Yeah, so I believe that a different shape of the droplet will affect the wave pattern on the surface, which will cause a different oscillation to be observed.
I mean the driving wave. Like if you put a triangular wave in the speaker.
Sorry, I'm gonna have to interrupt you there. We're a bit over time.
Okay.
I can see this going longer otherwise. Yep. 1 minute summary of the opponent.
Yes. Thank you, Team Singapore, for this discussion. I really enjoyed it, and I think it was very insightful, and we covered a lot of topics. We started out with the qualitative mechanism of why the waves form, and we concluded that it is because of imperfections and perturbations in the surface, which means that waves are formed instead of the droplet oscillating uniformly up and down. We also talked about the energies in the system and the energy dissipation, and I propose that the damping of the waves should have an effect on the eigenfrequencies, and then we also talked about the experimental investigation of the phenomenon. He had a nice phase diagram, and we talked about the oscillation patterns that he could observe. And from there on, we also talked about the transmission and reflection of the waves at the boundary, which we where we agreed that this should have an effect under some circumstances. And we also talked about the parameter variation, and I suggested to also investigate different viscosities and surface tensions. Thank you for your attention.
Thank you. All right, questions from the reviewer?
Okay, thank you, you two. So to the reporter, my first question would be, can you give us a number how many symmetry breaks you have so that the phenomenon of the worms occur? Just a number, please.
The number of, I'm not sure what you mean by the number of symmetry breaks.
Okay, to the report, to the opponent, do you understand my question on that case? Or can you give us a number?
I understand your question. So I think there's one symmetry break, so the perturbations on the surface of the droplet that cause the formation of standing waves. And then there's another symmetry break where a circular droplet breaks up and sort of
The answer is
stands
enough,
still
and I agree to you. To the reporter, you stated a short question. How many, or is there more stable frequencies or eigenmodes of the droplet itself inside the drop?
Yeah.
Okay, to the opponent, do you think it's appropriate, like the reporter did in his report, that he showed us, for example, a parameter variation that stated that they look at the stable frequency of the droplet. Do you think that's appropriate to then state there's just one frequency if he's stated that there are more?
I think there are many more overtones and stable frequencies. However, because of the liquid and droplet properties, higher stable frequencies are easily damped out, and it would have been really nice to see more investigation on higher frequencies, how they depend on parameters, surface tension, and viscosity.
Okay, partly on the opponent, because also the frequency of the eigenmodes of the droplet are also dependent on the shaker frequency. But we move on to your reporter. Have you accounted for vorticity since you have a small droplet?
Accounted for the viscosity of the droplet?
Sorry, have you accounted for vorticity, so vortexes at the
Yes,
edge of your droplet?
Yes.
Okay, because your theory states that you have no vortices. Your theory assumes that you have none.
No,
Okay,
I have solved the Navier equations to third order, so it does account for the vortices in the water.
Okay, and we just move on. Exactly. In your theory, how do you model the modes of your droplet?
We have used the Helmholtz equation here to model the eigenfunctions on the droplet surface.
Okay, I just wanted to get to the point that you say that you use Bessel mode, so I just assume, do you have used Bessel modes to model the modes inside your droplet, since you have a circular droplet at the beginning?
Yeah, we could use Bessel modes at the beginning, but this would not be applicable, for example, this pentagon. So we have to solve the Helmholtz equation for each possible droplet shape.
Thank you, I agree on that. That's a good point. If you go on, that's... sorry. To your experimental setup, you said that you used a speaker. How did you ensure that you have the same oscillation at all points at your container?
We have actually placed an accelerometer on our setup, and then we can ensure that the acceleration is uniform across the entire setup and that they are sinusoidal.
Okay, thank you. I think that's a good point, and it proves that your experimental setup is sophisticated. I think I'm out of time now. So thank you.
Okay, thank you. We'll get on to preparation for the reviewer. So you've got 4 minutes.
Okay, so hello and welcome. I will be the reviewer on problem number 7, Faraday waves. So we will just start right now with to the reporter. We can say that he had a really sophisticated theory, which was based on his Helmholtz equation, Navier-Stokes equation, as well on this pressure balance, which was really nicely done, as well as we can say it was really good to look that. But for example, if we move on to the science communication, we can say it was a bit improvable. For example, he had on the one hand really nice visualizations, but it was really he had a really fast pace, so it was a bit hard to follow as well. For example, that the references were stated that only at the end, so it was unclear what was his contribution on that fact. As well as if we go for example further, he showed us the investigation of the 3 different phases, or the 3 different shapes of the circular droplet, of the angulated droplet, and of the pentagon, for example, which was nicely done in one way, but on the other, especially, for example, when they were looking at the geometry. But on the other hand, for example, it was a bit he, for example, only investigated the critical acceleration, and it made a theory for that only for example, for the elongated drop. If we move on, for example, his qualitative explanation was basically almost completely lacking, especially for the symmetry break, as well as it seemed like the reporter wasn't really clear about which symmetry breaks even occur. Which was, as well as, for example, if you go on for the worms and the appearance of the Faraday waves itself were not explained at all. It was just stated, yeah, there are Faraday waves, but not explained why they occur. And that is even a symmetry break that they occur. So, for example, for an even surface, perfectly even surface, no Faraday waves would occur. For that was really important, especially as well that, for example, vorticity, he stated that were accounted, but on the other hand, inside his theory, he assumes that you have null vorticities. As well as, for example, he needed the amplitude for his Faraday waves, but hasn't shown at all how he investigated the amplitude of the Faraday waves, which would, in our case, we'd say really important. But if we move on to the opponent, he made a great summary of the report, as well as he showed a really physical insight, and it was really nice that he just shown us also later that the qualitative explanation, and it used the time to get somehow idea of what even happens inside these Faraday waves and what happens for the geometry. Now, if we go on, for example, also that it was a bit about that he spoke, for example, and bad point was that he, for example, he saw that the reporter didn't explain why worms occur and why the worms patterns occur, but they only described the real phenomenon at the end, why we have these small amplitudes looking at the form of the geometry, but he didn't really find the point, for example, what the real reason is, because the real reason is that the Rayleigh plateau instability at some point happens, and therefore, if we use, for example, an infinitely large droplet, at some point also the Rayleigh plateau instability would say that, for example, the droplet will split up itself into smaller droplets. Now, if we move on to the key discussion points of the position, we can say that at the beginning it was about the formation of the droplets of the Faraday waves, sorry, and we say that it was nice that the opponent showed, for example, that the explanation of the symmetry break, as well as it's good in our case that the opponent showed that it's due to these imperfections, and it was in that case really a relevant topic, but we missed the explanation for the resonance, why the amplitude increases over time, which is basically to the resonance between the shaker frequency and the eigen frequency of the Faraday waves, and therefore this was also completely lacking inside of the reporter. If we move on to the stability of the worm, we had the discussion about the worm-like shapes, which the reporter only barely explained that these worms, like he later correctly stated, that if you have this hysteresis when pulling back downwards, it was that it's due to this Rayleigh plateau instability, but it's also occur if the droplet just increases. Now, if we just skip that part, but it's because I see that the time is running out. And if you like to completely look at it, was from the report really done nicely that he investigated lots of cases, but this really qualitative explanation was lacking, and therefore as a viewer, one couldn't really get a feeling why Faraday waves occur, why we have these instabilities, why we have symmetry breaks, and in our case, we would say that's really important to understand as a viewer why that's the case, and therefore we also say that the opponent really nicely put out these points that this wasn't investigated. So thank you for your attention.
Thank you. And we will go on to clarifying or final remarks of the reporter once I have the presenter rights on whichever.
I think we don't need presenter rights for this.
Okay, go ahead.
Okay. So in summary, I believe that my qualitative explanation for the evolution of the droplet, that it will evolve to maximize the growth rate of the droplet is sufficient. And I believe that we have also agreed that the perturbations are important for both the Faraday waves to form and for the droplet to evolve and not to remain a circle, and that this is the origin of symmetry breaking. Furthermore, I have accounted for the viscosity and vorticity in my theoretical model by solving Navier-Stokes to third order, and I can predict the amplitude of the Faraday waves. I also agree with the opponent that we could have investigated different viscosity ratios of the droplet and the bath, but we were unable to do so experimentally due to being unable to find suitable liquids that would float on top of each other. Furthermore, I believe that I have sufficiently contributed to this problem by involving a transient simulation of the droplet evolution, and I believe that the worm should not have been investigated as it is not stable, and the problem statement asks us to investigate stable patterns. As such, I believe that I have sufficiently answered the problem statement since I have investigated numerous stable patterns such as the deformed and elongated regimes, as well as extended the problem statement to involve the transient regime, which is not stable. Thank you.
Thank you. Right, final stage, questions from the jury. If you have a question, feel free to raise your hand. Mohammed?
First of all, thank you all for the great fight. I had a question from the reporter. How do you think of changing the input waves, shape of the input waves, effect?
Wait, could you repeat your question? I didn't quite catch it.
You know, we have different shapes for the wave, triangular, a square. What
Okay.
if we change the input wave?
Okay, so I believe that any input wave could be decomposed into a sum of sine waves, for example, by using a Fourier transform. And in this case, then you will have to superpose the different modes that would result from those different frequencies that are forcing the waves in order to get the final droplet shape.
Okay, thank you. Thank you.
Ioannis?
Yes, I have a question for the reviewer. The reviewer mentioned in the review of the report that the reporter missed the point of the viscosity. So my question is, what would the difference be in the phenomenon had the difference in viscosity of those two fluids be smaller than the reporter used?
Well, the interesting thing is that if you have, if the viscosities go or the difference in the viscosity is lower, that at some point the lower fluid as well will, so we won't have a total reflection at the edge of the droplet, but the bottom fluid, for example, will start to oscillate as well. And for example, also that the threshold between the phase that the critical acceleration that that only the droplet have Faraday waves, and that the inside the bath also Faraday waves kind of will be smaller. So that's also interesting because at some point the Faraday waves will also occur inside the bottom of in the bottom fluid. So we have these two interesting things in our opinion, which the reporter could have investigated.
Okay, thank you.
Okay, I've also got a question for the reviewer. You brought up vorticity. How important is that? How much would that change the theory and results that the reporter presented?
Well, I don't have exact numbers, but I expect that since they used small volumes, so the droplet was really small, you can say that usually you assume that you have no vorticities, is that if you go into an infinitive large container. So that's the first assumption that breaks down so that you can say that there's no vorticities. And these vorticities will have an impact if you have a low viscosity. And like we used isopropanol, that's for example the case. And what I think would happen is that the critical acceleration needed that Faraday's will occur will increase if you have these vortices, because these vortices disturb the production of stable waves or standing waves.
Okay, thank you. Maria?
I'd like to extend the question to all of you, but primarily the reporter. If you could very briefly explain what is it that results in the formation of stable waves as opposed to unstable?
Okay, so what mainly results in the formation of stable waves is that initially the waves will be driven due to the fact that your system is oscillating. So initially your waves will be driven since there is energy input into the waves, but eventually you will get that there is a maximum wave amplitude because the viscosity of your fluid is actually damping out this energy input. So when the energy input is equal to the energy output into the Faraday waves, then they will be stable.
I think one important part is that to make the wave stable is that they are mostly reflected at the outer edge, so the viscosity difference needs to be very large. And then another aspect is that the droplet should that there should be no favored way of oscillation, because if there's one direction of oscillation, then the momentum transport of the waves will be a sort of self-positive effect, and therefore the droplet will expand and continue expanding, forming these worms.
So to give my comment to that, so at first it's the question of if you mean stable by the form of the geometry, that the geometry is stable, and if this only the Faraday waves are itself stable. For the Faraday waves, I would say the most important part is really that, for example, the viscosity, and that you go over this critical point of viscosity, so that you will see the Faraday waves. But if you also, for example, look at the worms itself in the geometry, I would expect that the worm slightly deviates by the geometry and are therefore not completely stable. As well, like we could see, for example, inside the hexagons, which like at the edge were a bit of like oscillating, and therefore we can say we have a lot of different parameters. For example, the density difference, the surface tension gradient between the two fluids, and therefore we have in that case a lot of different parameters affecting the stable patterns of the form of the droplet.
I believe I initially misunderstood your question. Yeah, so the main parameter that's controlling the stability of the droplet shape is the balance between the wave radiation pressure from the Faraday waves and the surface tension at equilibrium.
Okay, thank you all. That's the end of time for jury questions. We'll get on to grading and then inputting our scores in the system. Right, we have all the scores in from all the jurors for this final stage of the final. So we'll do the same as the previous two stages. So we will start with the reporter. So I would like to ask Young One to please motivate your lower end of the scale for the report.
Okay, I think that I just try to keep consistent with my previous score. Anyway, I think that the reporter did a lot of experiment and try to do some theoretical analysis, but apparently in the explanation, he didn't explain well how the wave were generated. And that I think we learned that only after the opponent and the reviewer mentioned about that. Okay, so that's the one of the main reason. And during the discussion, the boundary effect apparently not well described or discussed. Okay, so that I gave an average grade a little bit low. That's it.
Cool. Yeah, I mean, consistency is the key, especially in the final. And high for the report, we have Gyaneshwaran.
Yeah, so I found that the reporter has done a phenomenal work with the experimentation part. Lots of innovative methods used, like using a speaker to vary the amplitude of oscillation by increasing the loudness. So that they have characterized as acceleration. So, and that they are included into the theoretical model to describe why the change in shape of the droplet happens. So lot of creativity I saw in both the way they experimented and the clarity with which they have demonstrated the phenomenon and also the data and correlation with the theoretical prediction model. So, and explanations were also quite good.
Thank you. And for the opponent, on the lower end, we have Mohammed.
Okay, I think the opponent could lead the fight better, manage to use their time better. I think the questions were not in good order, good orientation, leading to something special. I think the discussion could be better.
Okay. And high for the opponents. One of them is me. So I like the report, but I wrote basic physics and I circled it 3 times as like, you know, qualitative explanation. And you spent a fair bit of time in clarifying like a bunch of things around that and what that meant, and I really liked that. So I scored you pretty highly on the discussion, and I liked the opposition speech as well. And for the reviewer, on the lower end, we have Yudong.
Okay. Yes, it's me, Flor. I think the reviewer gave the sorry, wait a minute. The reviewer gave the I gave the average grade for the reviewer because I think he gave the sorry he gave the advantage and disadvantage for the reporter and for the opponent, and I did not find so accurate so more point in it, so I gave an average grade. Okay.
Okay. And for the reviewer high marks, Sun Yu, would you mind commenting?
Okay. I think the reviewer was very good at
the role for the reviewer. So for the all sub grading section, I gave yeah a little bit high score than the average value. Yeah, that's why yeah maybe I'm the higher end. Yeah.
Okay, thank you. Thank you, jurors, very much for grading this round and all the other rounds in the final. And I would like to ask if all the jurors and teams, if you could unmute yourself and we can have a round of applause for all the teams for this final, because there was a lot of good physics. All right. So that concludes this. And I think we have a 15-minute break before we come back to this same spot and for the closing ceremony. So until then, go calm your nerves and see you back here shortly. Thank you very much for all the wonderful physics.
Yes, thank you very much. We will have a 15 minutes pause, and if so during the closing ceremony, we will go through all the teams according to their rank. And if the teams want to come into this BBB room via the virtual overview page, then they're happy to say a few words when they get announced. Then they can say like what they liked and what they learned, or something like that. Maybe it will work out, it will be nice, or maybe it won't work out and it won't be nice, but we will try it out. So anybody who wants to say a few words can come into the BBB room, and once you're announced during the closing ceremony, just say a few words. That would be nice. Thank you.
feedback.
So good morning, good evening, wherever you are, depending on your time zone. Welcome to the OYPT Awards and closing ceremony. After this amazing final, I'm not quite sure if we, like how long we're gonna stick around here. I know that the New Zealandian guys will probably want to head to sleep. So I will try to keep this in the beginning rather short. Of course, during the award ceremony, I ask everybody to give the teams another round of applause. So we'll take our time there. But first of all, the OYPT is now over already, which is unfortunate. It was a lot of fun. I mean, we're all happy to return to our normal schedule, but nonetheless, it is over. But we will see later that there is a reason to look forward to next year, of course. Before then, I would like to once again thank a few people. The special thanks from our side from like managing the whole tournament goes first to the fight assistant, to Tosuya, Izzy, Siddharth, Tianlang, George, Mattis, Fritz, Danny, Matthew, Johan, Benji, and David. Without them, it may have worked, but definitely not as smooth as it did. So most probably would not have worked. So thank you once again for volunteering and helping along with the fights and supporting our jurors and of course also the participants. Then among the jurors, there are also a few persons I would specifically like to thank because they took an extra workload, being both or all three chair, juror, and sometimes fight assistants. That is Chao Yang, Chi, Louis, Kent, Jung Yan, Jonas, sorry, this is a little bit strange English, Peter, Michael, Paul, and Yang Yu. So also thank you very much to those guys, because they took off a lot of work from our shoulders as well. All right, that concludes the special thanks. As I said, keeping it short. We will now come to the awards, honors, and special mentions. And as I said earlier, we will go through the teams by rank, starting from the bottom. And if you would please, like for each team, unmute yourself and give them a round of applause, that would be great. And if the team is here in this BBB room, they're also happy to unmute themselves after the applause. And if they want, they can say a few things. We will see if the teams actually want to do that. If not, that's fine as well. But if you want to say a few words, then that would be also quite nice to have. All right, I'm just going to switch presentations. So we're going to have participation awards for like half of the teams. Then we will have 6 bronze medals, 2 silver medals, and 1 gold medal for the winning team. Of course, we won't have real medals because we're just an online competition, right? But you will receive certificates after the competition as soon as I'm getting back to Germany and find the time to take care of it. So there will be something official. I hope you're looking forward to it. And other than that, of course, the most important thing you got from this tournament was, of course, hopefully the experience and learning something new. I guess I've learned a lot of things, especially in the final, which was amazing. But all right, let's go on with team. This takes a long to load. Team Iran on rank 18 with 86.7 points. So Artin, Abbas, Sarina, Mohammed, and Rohan. Thank you for participating. Can we have 2 more people? Thank you very much. Thank you very much. So if you want to unmute yourself and say a few words, that would be nice. But otherwise, I'm going to continue. Artin is writing in the chat. You're the first team, so we know.
Can you hear me?
Yes.
Yeah, I want to first of all say hello and hope you feel great. How I said I'm Artin Radmatin, captain of Iran Team Ballet. In general, it was very good and sweet experience in my life. And also it's very more attractive for me because I'm just 13 years old and I think I'm in the lower age category of this competition. And it was a sweet experience for me at this age. Thank to all those who tried to hold this competition.
All right, very impressive on your age. Thank you very much for participating. We will go on with the next team on rank 17 with an 89.8 point team Australia B with Asha, Sophia, Adrian, Anthony, and Hugh. All right, we will move on. Team India on rank 16 with 111.8 points and even more impressive, 2-1 rounds with Akshat, Pune, Keshav, Yuf, and Shikha. A round of applause, please.
you want me to proceed?
If you want to say something, sure, go ahead.
First of all, namaste from India, respected ladies and gentlemen. I'm Akshat, and on behalf of Team India, I wish to convey that it was indeed a very exciting and memorable experience for us, having become participants of this tournament. I wish to express my warm gratitude towards the organizing committee for the immense efforts being put forth for a successful conduction of the tournament. I wish to thank the jurors for reviewing and judging our work and providing constructive feedback, which was immensely valuable for us. I'd also like to thank my fellow teammates, Mr. Shashikant and Mr. Gyaneshwaran, without the efforts of whom it would have been impossible for us to participate. Our participation and our preparation for this year's OYPT comes to an end after a lot of learning having taken place, which was overwhelmingly fruitful and enjoyable. Because at the end of the day, that's what matters the most, right? Having learned a lot and having met a lot of awesome people at the forefront of the field. And finally, having produced something original, generally speaking, as an effort to move ahead on a rather long and exciting journey filled with countless endeavors and to be able to contribute in some way for the benefit of mankind. Thank you very much again, once again. It was a pleasure being here and having met a lot of people, all of you in general. I look forward for the next appearance of Team India in IYPD 23, of course, with an improved performance. Best wishes to everybody for their endeavors ahead. Thank you.
I couldn't have said it any better. Thank you very much for those words. All right, on rank 15, we have Team Hong Kong. I think it's the first time participating at an IYPT-like event. They've won one round and achieved a total of 120.1 points. So it's Varun, Grishif, Roshan, Yingyun, and Edward. Thank you. A round of applause. And then we have on rank 14, we have the team Australia, so the primary team with 127.7 points. And one round one, we have Carmen, Emma, Owen, Tom, and Alan. Please, a round of applause.
Hi everyone, my name is Carmen and I'm team captain from Australia. Just on behalf of the team, I want to thank everyone involved in making this competition as amazing as it was. We very much enjoyed the experience and learnt heaps along the way. Thank you.
Thank you as well. And continuing on, we have Team Greece on rank 13 with 128.9 points, and round one with Jonas, F. Stratios, Petros, and Marios.
Thank you, everyone. I'm Ioannis, from the team captain of Team Greece. And we would like to thank everyone for this participation and the amazing chance that you gave us to improve ourselves and have this wonderful physics fight with the other countries and make new friends every time. Thank you, everyone. I hope to see you soon next year.
I hope we see each other too as well. Then on rank 12, we have team from New Zealand with 129.9 points, and round one, we have Tide, Ramanujan, Ethan, Vipya, and Sean.
It's been such a fun tournament, and I think we've all learned a lot. So thank you.
Thank you as well. On rank 11, we have Sweden with 133.0 points and round one, which has Bahar as captain, Linnea, Hugo, the Destroyer, Ilya, Morris. A round of applause.
So I'm Bahar, team captain from Sweden. On behalf of our team, I would like to thank you for all the great physics fight and constructive feedback given from the jurors. And I would also thank my fellow teammates, Linnea, Hugo, the Destroyer, Morris, Ilya, and we very enjoyed OYPT and look forward to future competitions and seeing you all again. Thank you.
See you in the future. Thank you very much. I think with the following ranks, we will give out bronze medals. So there was a big gap in the partial points between rank 10 and 11, and it also fits kind of the number of bronze medals. So that's why we decided to cut here and go on with the bronze medal. And the first bronze medal goes to the team of Korea Tae-geok on rank 10 with 135.2 points, free rounds won, with Seongmin, Wongi, Yong, and Jaeyoon. I'm sorry. A round of applause, please. And the second bronze medal goes to the team of Field of Experiments, our internationally mixed teams on rank 9 with 157.3 points. 4 rounds won, containing of Daniel, Alexandra, Kirill, Anton, and Alexander.
Thank you everyone for this amazing opportunity to exchange great research ideas, and we hope to see everyone next year as well, according to plan. Thank you very much.
Thank you as well. On rank 8, we have the next bronze medal for Team Brazil with 159.6 points, 2 rounds won. It's Alvaro, Miguel, Guilherme, Livia, and Vitor. Thank you very much.
Hello, I'm Mauro. I'm captain of Team Brazil, and I just want to thank you all for this great experience. I really enjoyed it. I want to thank the flight assistants, the jurors, everyone, and I want to give a special thanks to Bismarck, Gabi, and also Menegon, who would help us in this competition. Wow, thank you very much.
Thank you as well. We move on. Rank 7, Team of Korea Arirang, with 162.2 points, 4 rounds won. We have Youngwook, Yoonmin, Yeon, Sunjae, and Jisung. Thank you. Round of applause.
Hi, my name is Youngwook Kim. I'm the captain for Team Korea Arirang. I'd like to first thank everyone who we met, who didn't meet during the tournament, for all of the great physics that we got to experience, and also I'd like to thank all of my teammates for the wonderful 1 month we had preparing for this tournament. Thank you, everyone.
I hope you had a lot of fun. Moving on, rank 6 goes to the team of Chinese Taipei, or rather Taiwan, with 175 points, 170.5 points, 2 rounds won. We have Yisheng, Ling Xuan, Vincent, Anna, and Hardy. Thank you.
Okay, hello judges and other competitors. We are Team Taiwan, and I'm the captain of the team, Ethan Xu. First of all, I would like to thank all the organizers for the preparation of the competitions, and also thank all participants who discuss physics with us in these competitions. And this is a very inspiring experience, and we are honored to take a part of it. Thank you.
We were happy to have you. We move on to rank 5. Team China with 170.7 points, all rounds won, which is a bit unfortunate that there is no additional OYPT rule for advancing into the finals in that case. We have Jingyang, Andy, Hawks, Yu Jong, and Kim Yao. A round of applause. And then moving on to rank, now it's getting complicated, right? So, and for now, as you've probably seen for the ranking, we had 2 Singaporean teams here, and the medals go out as follows. So the winner of the tournament takes the gold medal, and the 2 other finalists take the silver medal. But we also had a 4th team, let's go with that, who would have advanced to the finals were it not for a special rule at the OYPT to ensure that the IYPT transition of it being a competition between countries to be just to keep it up like it's usually, even though we allow multiple teams from one country. So we would like to give out an honorary silver medal to the team of the secondary team from Singapore, who ranked 3 in the preliminary fights with 181.7 points. All rounds won. It's Yin, Min, Keru, Yudi, and Vera. So a round of warm applause for the team Singapore B. And that leaves us with the placement of the final teams. So of course, this is unknown. I had to look it up, otherwise I would have been like, I didn't know if whether the presentation would be correct. So we will move on also from the bottom up. So third place, second place, which will also of course define first place, and then the first place who won competition with the gold medal. So long story short, on third place, we have Team Austria in the final rank 3 with 40.5 points. It's Elias, Jeremiah, Marcus, Johannes, and Anissa. It's a big accomplishment. Do you want to say anything?
Yeah, hi, I'm Jeremias Costa from Team Austria. Sadly, 2 of our team members already had to depart for the flights back since we're here in Sweden. I would like to say some thanks for the organizers of this whole tournament and also for the meetup for the meetup in Sweden. I would also like to say some special thanks to our team leaders, Michael, Paul, and Martin, since they've helped us so much with our preparation, and a special thanks to Thailand Algan, who has helped me with my presentation, for example. So thank you for everybody involved. We had a great time, and it's of course always great to bring back an accomplishment back home. So thank you for the great finals, thank you for the great physics fight, and thank you for everything.
Absolutely no problem. It was a nice presentation. Was great work in the finals as well. Now it's getting more. Now it's time, right? So we will announce the rank 2 as soon as Maria is muted. Okay, thank you very much. So we will go on to the final rank 2, which is Team Germany with 42.8 points. It's Louis, Tarek, Florian, Luan, and Maya.
Hi, here's Louis Liemstein, and I think I can say that I really enjoyed everything here. I think I can speak for the whole team if I say that we had a great experience, and all of us, I think, learned very much and will behold this whole event in great memory. So thanks.
All right then, now it's not a surprise anymore, so let's just go on. We have Team Singapore on final rank 1, winning the tournament and the gold medal with 45.7 points. It's Luke, Martin, Yuns, Hillary, and Ong Jion. So a big round of applause for the winners of the tournament, Team Singapore.
Okay, we would like to thank everyone, jurors and opponents, for all the physics discussion and the physics fights. We found them really, really fun. So also a very big thanks to the organizers for making this possible. So we hope to be able to see all you guys again next year, either in OYPT or IYPT. Yeah, bye.
All right. I sure as hell hope that it will be an IYPT. And while we're on the topic, we will switch back to my other presentation because there are next looking forward to the future. While we're on the topic of the IYPT, I thought it would be nice to give you an idea on what happens next year, because I hope that the OYPT has motivated you to continue your research on the IYPT problems and possibly try again for your national selection tournaments. And possibly we will see each other next year. Next year, the IYPT will happen in Budapest, in Hungary. So I will just give you a quick, introduction on what will happen to make sure you're staying motivated until next year. It will happen in Hungary. As I said, it's part of Europe with a nice weather apparently in July, so about 35 degrees. So maybe we can take a dip in the water. I'm not quite sure if you should swim in the river, but I'm sure it will be a nice opportunity to hang out together and do some physics fight. It will be hosted at the university, ELTE and BME and there should be a picture on the slide of the campus. No? Well, not in this case, apparently, but everything will be close together, so it will be quite convenient to walk around, hang out, do the physics fight, and chill out in the evening. So I'm sure it will be a great competition, and I hope as many as possible of you can come. Then, now everything crashed on my end.
Hi, it looks like Michael is not able to continue the ceremony. So I'll just quickly take over. Is that fine? The preliminary schedule was a bit shifted forward regarding to the other IYPTs, which are normally later in July. This is to not collide with the International Physics Olympiad, which happens directly afterwards, and it's always displayed. So it's a bit earlier, but it should not be a problem. The new problems were decided at the IRC meeting 2 weeks ago now of the IYPT. They are a bit preliminary because they have not yet been fully checked for language, but the main idea of the problems is already fixed. You can get them on the official IYPT page, and you can start working on them as soon as you want. Okay, Sam checked the language, so probably they're okay. They just normally we release them as a signed version by the SecGen, and this has not happened yet as far as I know. But with this, it's sad but over, so I'll just take over from Michael and declare the OYPT closed myself. Thank you all very much for participating, and have a nice day.
Yeah, thank you for taking over. All right, sorry about the small technical issues. Hopefully we'll see each other next year. See you then. Bye-bye.
See you next year.
Bye-bye.
Bye.
Thanks so much. Goodbye.